introduction to how to use Crowdcast after we do that. So why don't we go ahead and go first? Jeff, you want to go first? Introduce yourself?
Sure. My name is Jeff Erlich. I'm an assistant professor at NYU Shanghai. I'm in Shanghai, China right now at 2 p.m. My lab works on mouse, rat, human, and synthetic subjects. And I would say that most of our modeling is at the cognitive behavioral level, but we also do some attractor network type dynamical systems modeling. But I would say I sort of almost consider myself like a cognitive scientist these days, just thinking about like the algorithms of behavior rather than the details of how the neurons are doing it.
Cool, thanks. And Arvind, you want to go next?
Yeah, sure. Hi, my name is Arvind Kumar. I'm based in Stockholm at the Royal Institute of Technology. I'm a computational neuroscientist, and I have remained computational neuroscientist since my PhD days. Before that, I studied electrical engineering, and then I don't know how I managed to get into neuroscience, but this is so much fun. When I switched, neurons pretty much look like electrical devices, and that was my entry here, and I have stayed with that idea still. I think there's so much to learn about properties of neurons, not as individuals, but as part of networks. So that's what I've been doing for the last 15 years or so, trying to understand the properties that the neurons' connectivity renders to the networks. So I'm really at the hardware level and trying to understand what it means to connect neurons, and then some function emerges in that network.
Awesome, thank you. And Ulrich, you're next.
Right, so my name is Ulrich Beierholm. I am an assistant professor at Durham University in the north of England. And I am in the psychology department, and I work mostly with humans. I do modeling, computational modeling, of course, of different types of behavior, most of the cognitive type of stuff. And we use, partly behavioral stuff, partly EEG, partly fMRI, basically whatever kind of fun tools we could get our hands on, and try to model partly perception, partly reinforcement learning, part of decision making too.
Cool, thanks.
And I'm sitting in my garage right now, as you can tell.
You're what? Sorry?
I'm sitting in my garage right now, as you can tell.
Your home office, right? Yeah.
Cool.
So, and everybody, I think, probably knows who I am now, but my name is Megan Peters, in case you guys missed it. And I'm an assistant professor of cognitive sciences at UC Irvine. So there was a bit about that in the welcome video, but maybe that was a long time ago by now. You guys, your brains are probably very full. And so just to remind you, I work on human neuroscience with fMRI, EEG, and computational modeling. So what we're going to do now is we're going to do a little bit of discussion. So at the end of the video that you guys all watched, we talked about the modeling goals and how there was this massive diversity of goals in different models, and how all goals are good and valid and just are different from each other. And so what I'd like to do now is we're going to put one of those slides back up on the screen, and we're going to do a little poll so you guys can vote on which of these 12 goals you think are the most important. And you have to just pick one, okay? Just one. I know that's kind of not fair, but let's just pick one. So I'm going to have to kick one of you guys off screen here. Who should I kick off? Sorry, Arvind, I'm going to kick you off. And so now I'm going to share my screen. And I'm going to allow this window here. Can you guys see this? I think you can see it.
Not yet.
No. Okay. Well, I didn't check my stuff before, so I guess that would be different. Oh, well. So let's just put the poll up, and we'll do it this way. So let's put the poll up. So you guys should be able to see the poll now, I think. No?
Well, I can't. Maybe the other people can.
Can you guys see a poll? Can anybody?
Oh, there's a poll link at the bottom.
Yeah. So if you go to the polls at the bottom,
Oh, yeah. I see it.
Here.
You can like click
and
it.
you guys can click on that and you can pick which one you think is the most useful. Okay. And so you can actually watch in real time which of these goals you think is the best one. So sorry, I don't have any slides for you guys. Well, you guys are doing this. Let's see if I can fix that.
What's the goal of modeling?
Yeah.
By having real-time feedback, it can bias future voters. They're like, oh, do I want to be part of the crowd or do I want to be different?
That's true. That's true. So try not to look at, what other people. A lot of people like useful models. I suppose that's useful, but also interpretable. Interpretable seems to be very popular. Okay, interesting. How about you guys? Do you guys think that any of the which one do you think is the best one?
I think a normative wasn't getting enough love right now, so I
All right, I'll switch mine to normative too. You can't switch.
Okay.
I mean, useful is very broad.
Useful is very broad. Yeah. Useful is good at solving real world problems, right? Like we're not really sure what those problems
mean.
Huh?
Is that what useful means? Real world?
Well, these are the things that we put up in the slides, right? Like good at solving real world problems. Like maybe there's a real problem to potentially solve.
Oh, I see.
Okay.
Inspiring experiments is obviously something that's really important too, right?
Yeah, I think
it's nice when a model can describe all the previous data, but if it actually gives some ideas of something new we can do, some new experiments, then that's awesome.
Yeah, I think that's really important too. That's one of my favorite things to do with models, actually, is you kind of say, okay, I've got this model and it has behavioral realism and that's wonderful. But then if I push on the model in this particular way and I break it, then I can design an experiment and try to break the human in the same way or break the brain in the same way. And I think that that's really fun because then if your human and your model break in the same way, then maybe you got something right.
Yeah.
So that's pretty cool. All right, cool.
Breaking brains is pretty fun.
Yeah. Okay. Well, I'm going to bring Arvind back on the screen here because apparently I didn't get my screen sharing working right. So that's too bad, but we'll have to make do. So Arvind, welcome back. He's connecting now.
So interpretable one.
Interpretable one, huh?
34 votes.
It did win. Okay. I wonder. So if you guys have any questions about that also, like in Crowdcast, you can click the Ask a Question button at the bottom. And that Ask a Question button will allow you to actually ask specific questions. Then other people can upvote them. So people can vote on what is the kind of most important one. Okay. So the thing that I'd like to do first before we do that, and I really apologize for the screen sharing not working, guys. So I'm going to just have to talk you through it and you will have to bear with me. But I hope that everybody is in NeuroStars. Have you guys hooked into NeuroStars? Everything is working there. You can respond in the chat and let me know. Is NeuroStars good? Yes, no, kind of, maybe. Maybe. Come on, guys, in the chat. So if NeuroStars is working okay, sweet. Okay, so if NeuroStars is working okay, at the top of your NeuroStars categories, there are these links for surveys, and you should see this whether you're either an observer student or an interactive student. So there's these surveys we're calling them reflections, okay? And so the reflections, the idea here is that we want you to take a moment to kind of think about what we did today. And we know it was super fast. We know that it was super intense and that you had a nice break in the middle where you maybe got a chance to eat some food and then you came back and did more intense stuff. And so these reflections, the idea is to think about what did you know when you came in to today? What did you have a background in? And then what did you leave with? Did your thinking change? Did your ability to apply these ideas in your own research change? And so if you guys can go into NeuroStars, and again, I'm sorry I can't share my screen, but if you can go into NeuroStars and you can find at the top of NeuroStars, in the interactive students or the observer students category, you have a little drop-down menu. And then you'll have a daily student reflection link and information. And if you can go in there and you can click on the link that goes with your pod, essentially. So you drop down in the survey, your pod, and you tell us what you think. And there's another thing that's really important about these surveys that we want to tell you about too, which is that this helps us figure out if your pod is working well together, if you have good communication, if you're able to find everything that you need, all of that good stuff. So if you want to take a moment now and just click around in NeuroStars, and if you're lost, please let me know. Let's see if we've got some questions about this. Does not look like they're all about the tutorial so far, so that's good. Nobody's lost. Fantastic. And we'll get to these questions in a second. But if you want to take just a couple minutes now while we're kind of chit-chatting about these goals, to think about what you did today, to think about what you came in with and what you came out, what you left with, and then I can also post the links in the chat. I suppose I can do that. That would be fine. And so I will do that right now, and that will help. So here is the link for the interactive students, okay? I'm putting this here. This is for the interactive students. And then this is for the observer students, okay? So if we've got some observer students here, you're also encouraged to do this. We know you don't have a pod, but that's okay. We're still really interested in what you guys are thinking about this. And so this helps us make NeuroMatch Academy better for the future and so on. So here's all the links in the chat. You guys can go and do that. And while you guys are doing that, we can continue talking, maybe take some of these questions that you guys have done. So so we've got
Can we see the questions? Or
I think you guys can see the questions too. Yeah.
There's a
So
link
in the
at the
ask a
bottom.
question at the bottom, and people have
there's a separate tab. I
Yeah.
see. Okay.
So we've got some questions about the tutorials, and we can try to do some of those, but we also want to do some big kind of overview questions. And so if you do have specific questions about your tutorials, a great thing to do is to actually ask your TA, because I bet you there are a bunch of other people in your pod who have a very similar question, and then you guys can have a really great discussion about it. So here's a question at the top. As we were looking at the neurons one by one, there are many neurons behaved exponentially distribution-like, but there are also that kind of do something different, right? Neurons that kind of behave more uniform distribution-like, meaning their spike counts are a little bit more uniform. So what are the possible mechanisms for this? And we've got some nice answers, some nice comments about this, but do you guys want to do any of this? Anybody have some ideas?
I mean, I've never seen a neuron with a uniform ISI distribution.
Yeah.
So I'm a bit confused.
So yeah, it's about like whether it's a spike rate or whether it's an ISI, right? And so this would be, I think this is for ISI, like the mechanisms. I do feel like it would be very difficult to have a ISI distribution that would be kind of uniform.
Right. You could have something a little more flat, gamma or Gaussian. So like anything that's like a pacemaker will look Gaussian, basically. Like it'll have a peak with some noise. And the information content there is pretty low. It's just like a clock ticking.
Yeah. Okay. So let's do that one. The second one is kind of very similar. I think. And so I think that let's go to the third question here, which is like the match. This is kind of a broad overview question about like the what, the how, and the why models, right? How to reconcile the models. How do we reconcile the models between, especially tutorials 2 and 3, the how model and the what model and the why model. So this question comes from Yian. Maybe you want to come up on screen and do a little more, or would you rather just stay in the chat? We can do it either way. I can actually call people on screen if you guys are feeling brave. So if you're up for it, we can do that as well. So Yi Yan, if you're here and you want to be on screen, just say so in the chat and I can call you up. So I think it's kind of interesting to think about like how to make the models consistent with each other. I kind of think you don't need to make them consistent. I think that a single model can do kind of multiple heavy lifting. What do you guys think?
So sorry, I haven't seen the tutorial. Do you mind explaining a little bit more what, why, how, and what?
Yeah, sure. So I had these cute hats. Oh, maybe I still even have my hats. And Konrad had some cute hats too in the tutorials. But the idea is that the type of model that you're building depends on the type of question that you're asking, right? And so you can have a descriptive model, which is you want to find the best description for the behavior, but you don't really care about how it works or why it does it that way. How model then would be more like a leaky integrated fire or a Hodgkin-Huxley kind of approach, where you're saying, okay, what are the mechanistic reasons why the system behaves in the way that we've described it? And then the why model is, why did the system evolve this way? So this is kind of a normative question. So they kind of map onto Mars 3 levels, right? Yeah,
it sounds like it.
A little bit, except for the descriptive level model doesn't really quite fit in the thing, in the hierarchy. So I think they don't need to necessarily be consistent with each other. They don't necessarily need to be separate either.
But I mean, if you want a full understanding, you need to like have maps from the concepts in one level to the concepts in the other level, right?
Yeah.
And I think this is actually like one of the biggest challenges sometimes when like neuroscientists talk to the public or to psychologists. Like when we say memory, maybe we mean like persistent activity. But when a psychologist says memory, they're talking about like the experience of remember, like, you know, there's this, we use the same word, but there's actually like a pretty big conceptual gap sometimes between the meanings. I think it's a real, I mean, I consider this one of the great challenges of any science, is like how you bridge conceptual levels. Like how do we, you know, that's, it's a real challenge. I don't know if that's not helpful.
But I think I'm with Megan on it. There's no reason why they should be reconciled, because every model you construct to answer some questions. It depends on your questions, which level you want to explain, whether you are happy with a why model or a what model or how model. Sometimes, if you just let me indulge a little, I think it goes very way far to Aristotle, who's thought about like what is explanation, right? And he talks about different kind of explanation, like whether it is an efficient cause, whether it's a causal explanation, it's a material cause, it's a formal explanation. So he talks about these different levels. Some of them are like when we talk about a mechanistic explanation, then we really want the model to answer questions related to the hardware of the brain. And this is useful when you are thinking of clinical explanations. So in that sense, it makes a lot of, it's pretty good to have a Hodgkin-Huxley model, right? If you want to control the neuron spiking behavior. A leak integrate fire neuron would not help in that. But if you're only interested in, you know, that, yeah, there is a spike occurring, or I'm only interested in ISI interval distribution, then leak integrate fire neuron is perfectly fine. You can talk about why it should be, right? That's the formal cause in Aristotle's sense. I don't think there is a good answer for it. For formal cause, we always come up with our own expectation.
I definitely think it all comes down to the question, right? And this is something that goes through both, like whether you're doing experiments or whether you're actually doing modeling, right? It's about the question, and something that, you know, we have to tell students over and over again. Of course, you know, what's the real question that you care about, you know? And that really should be framing your entire thinking, whether it's modeling or experiments that you're doing.
Sometimes your question, though, it ends up falling into multiple categories, right? Or the model that you build falls into multiple categories. And so maybe that's like this kind of consistency idea, is that you come up with a model that can bridge the gap a little bit. And this is why I think we should not try to force models into this like what, how, why. And that's why we also talk about Mars 3 levels of analysis as another way of possibly categorizing models. And then we also think about like levels of abstraction, which is like, neurons all the way through people. That's another kind of way. You can have mechanisms in people, and you can have mechanisms in neurons. So maybe that's kind of how we should think about this a little bit.
Can I ask Arvind a question, actually? So if I'm, let's say, like a pharmacologist, and I'm trying to come up with a drug that like cures epilepsy, let's say, like, is that kind of goal? So for a model that like predicts whether a drug is going to work is a useful model for that. But does that really apply to Mars? Is this something that I feel like Mars levels is more about like gaining explanation or gaining understanding, not so much solving like an engineering problem? Because he's talking about the goal of the system rather than like the goal of the scientist, right?
Yeah, but I think we can hack Mars' approach a little bit in this, because if you now define epilepsy as somehow instability of the system, right? So that's then becomes the
goal of stability.
If stability is the problem, right? So I don't know what stability is needed for, but that will be somewhere a requirement at the algorithmic level that the system should be stable. And then you can go down at the implementation level that how is this stability being implemented, and there comes out your drug then. So I think this is how you could hack a Mars way of thinking for this.
Yeah, it's a great answer.
I like that though, because it kind of shows that you can have a set of goals. You don't have to have just one. I know it was kind of like fake that we were like, oh, pick just one that's like the most important in the poll, but you can have this set of goals. That you have a train of goals or this kind of cycle. And I think this is part of what's going to be talked about tomorrow in the modeling process too, which is like there's this cycle of like, okay, once you've done the testing and the publication, now what? Now you go back to the beginning. And so then you ask a different question maybe about the same system. Cool. Okay, what other questions? You guys got any questions in here that you particularly want to answer? Because you guys can see these too, right?
Scrolling through.
Yeah. So, here's one that I like. What is the main purpose of computing entropy when comparing models? So this is actually a really good question. The main purpose is to see whether entropy ends up, this is one of the main purposes, is to see whether entropy ends up being able to differentiate between models. Because if it does, and one of them maximizes entropy, then you know that this is kind of a normative model. This is the best mathematically that a particular model could do, or that the system could do by this metric. And so we use entropy to compute the information in the system, but you could come up with a different metric too and see whether the model that's the best under one metric ends up being the best in another metric. And so one of the things that we'll talk about over the next couple of weeks is model comparisons, model fitting and model comparisons, and how if you want to pick like the best model, then best is all relative, right? Best relative to what? You have to like decide on your loss function. You have to decide on what loss function the system is using. I know that everybody here fits models and has done comparisons across loss functions and those types of things. Ulrich, I know you've got some papers about that.
I've literally spent years doing those kind of things.
Yeah.
I want to add one more thing here, because in this question, there's one line which says, do you mean if ISIs become bigger, the exponential will not be the best solution? I don't think this is correct, because in a way, and you want to use this class of models like maximum entropy model, their exponential pops out because you are fixing a firing rate, meaning you are saying that my mean interval is this much. And then if you don't assume anything else, then the exponential distribution turns out to be the with the highest entropy. So ISI being big or small has nothing to do with the shape of the distribution.
Awesome. Thanks.
Although you do run up against the refractory period at some point.
Oh, great point. Yeah. Yes. Clearly this idea that neurons are Poisson or renewal, that doesn't hold, right? So you will end up with some kind of correlations in the time domain. Absolutely. I think we forget this when we go on to the Poisson track and exponential distributions, then we forget that neurons have refractoriness. Yeah.
Awesome. Okay, well, we can make our way through these. These questions are great, guys. Keep them coming.
There's a question about like, how do you know that your neuron is that your spike comes from? Oh, it seems like I got cut off for a second.
Oh,
Can you still hear me?
Hear you? Yeah.
Okay. Let me see if I can recover this.
Technology.
So the question is about like, how do you know a spike comes from a single unit versus like a single neuron versus not?
And like neuropixels.
Or in any spike recording system.
Yeah.
And I think the answer is it's a real tough problem. Like it's relatively unsolved. The spike sorting problem is a continuously challenging problem. There's very few data sets that give us ground truth because you have to do like an intracellular recording at the same time as a extracellular recording. And so we do our best, but I don't know if there's a universally agreed upon kind of solution.
Yeah, I don't do spike sorting myself. I work with some people who do, but I think you're right that this is a really hard problem, and generally the kind of logic is if you see two spikes too soon, too close together, then they're probably not the same neuron spiking twice really super fast. And so this is like because of the refractory period, right? And so then you think, okay, well maybe this electrode is listening to two different neurons. And so this is in response to this question by Yan Ming, who is asking, how do we tell whether it's a single unit or a multi-unit, and also like what's the difference between a unit and a neuron? Here, it's kind of they're usually used interchangeably in this kind of context, but you still have to figure out whether the spikes that you're seeing are coming from like one unit or several, and that's a hard problem. And there's a lot of people working on it.
There was a nice paper though saying that not all analyses are particularly sensitive to the answer to that question. So I think from Krishna Shenoy and some of his friends, maybe Mark, there's like a neuron paper basically doing population analysis, not worrying about spike sorting at all. And depending on your analysis, you get a lot of pretty much the same answer.
That's great. That means that your question and the way that you're going about it is kind of robust to the assumptions of your analytic pipeline, which is not always the case.
Robustness is actually something we really, as modelers, need to care a lot about, right? Like, we need to make sure that our models are not super sensitive to small details in parameters, for example. So that's an important issue.
But this discussion about spike sorting and whether unsorted spike trains are also useful, I think this also has something to discuss here, that from an experimentalist perspective, treating a multi-unit spike train is totally fine because your goal that time is to link some behavior to neural activity. Now, this becomes a great modeling challenge now if you treat that multi-unit activity as a single unit activity, or you treat it as a multi-unit activity, meaning many neurons are contributing. So building the mechanistic models becomes simulation gives you a more centered distribution. What you need to understand is that how a neuron spikes in this case. In leaky-integrated fire neuron, it sums up inputs and then it hits a threshold. If you only excite the neuron, then your in-membrane potential goes above the threshold and then it just keeps spiking because there is nothing else it can do. So this we refer to something as the mean-driven stage, where the mean membrane potential is above the spike threshold. That every time, basically the driving force from the neuron is not enough to do that spike, and it will just spike with respect to concentration. But if you add inhibition does two things. One, it reduces the mean of the membrane potential because excitation and inhibition are negative. However, when you add these two, your fluctuations become very low. So what happens when you add?
Hello. Okay. I'm really? I can hear you, but it is kind of coming in and out. How about Megan? Weird. Oh, so I can just monologue for a while. What were we talking about? I was busy trying to solve my webcam problem. Okay. Sure. How do we know that our model is correct? All models are wrong. Someone already wrote that. All models are wrong. Yeah, so that's a great question. It's a great question. Oh, the model is right, but reality is wrong. I follow Andrew Gelman, who's a statistician at Columbia, who's one of the authors of the STAN modeling program, and I think he has a lot of good advice on these types of questions. He has a great blog, Andrew Gelman. There's a lot of funny. Oh, look, he has the book right there. Bayesian data analysis. I'm getting a lot of like thumbs up in the chat, like, hey Jeff, just keep going. So right, I mean, so when I was an experimentalist during my PhD for the most part, and during that time, I saw the main point of models is that it forces you to quantify your hypotheses. There's a lot of, if you don't have a model, then you're just using words, and words are easily misinterpreted. But if you have a model, it's very clear. You have quantitative predictions. It forces you to be careful. And then I joined Carlos Brody's lab as a postdoc, who's a pretty well-known computational neuroscientist. And we were reading papers on attractor dynamics. And I just felt like all of these toy models where it's like a two-dimensional, like we know the brain is not a two-dimensional attractor, because that would be pretty boring. So what do we really gain when we say like there's a like we say it's biophysical, but it's so simplified that it's like very abstracted from what's real. And I struggled with like, how do we know when we're like really learning something from our modeling and when we're not? I guess people are going to try to reconnect while I keep going. I'm somehow the only. No, apparently you're not even live. It's just like only me.
I tried to read.
Oh yeah, so people are asking for it's Andrew Gelman is I think he's got a blog. I think. Okay, so Konrad's just saying like keep going. Okay. Oh, Arvind's back. Great.
I tried to reload because that's what Konrad said.
Okay. So Megan, if you reload, we're all gone. We're all goners. Megan cannot reload. What you can do is join on your phone or something. No, then just mute your other thing. Yeah. Okay, so let's see what other questions do we have. Right. So there's another question actually, which actually I think is a really important question, which is when we don't know the ground truth, how do we know if our model is good? And there's actually a good answer to that, which is always generate synthetic data. So whatever you're trying to model, always make data that you know what the true parameters are, and then generate a data set which has all the properties that your actual data set has, but where you know the truth, and then fit your model and make sure that you can recover the true parameters. If you don't do that, I'm probably not going to believe your results. I hope I haven't offended anyone. Okay. So Arvind, do you want to pick another one?
Yeah, I'm just looking through it. Have you noticed something interesting that I could take?
There's a lot of questions about like ISI, and there's a question about the relationship between entropy and information. Why do we use Poisson distribution? Oh, super good. I'm wondering whether computational neuroscientists suffer a lot during the time in which your model does not match the experimental data at all for a long time. How do you get through it? Yeah.
Okay, I think so. I can say something about it. I don't know if it's a good answer, but we can take this up. Obviously, it's a good news when your models are not fitting the data. So that means that you need to revise your thinking, and you need to define better models that will match with the data. So that definitely is not. It's definitely not a bad thing that your models are not fitting the data. Now, what do you do in that case? You can always fall back to the normative side, that you try to refine your models. You try to come up with better arguments, because if data is not fitting to models, there are two problems: that your models are wrong, but also it's possible that the data is wrong. We are measuring something that is not useful. this continuous interaction between modeling and data. It's not a one-way process that you get the data and you model it. Your model should also guide the data collection. So I think this interactive loop should be activated more and more rigorously and vigorously when there is a mismatch.
Yeah. But I think that in general, scientists are kind of long suffering. Like, if you don't have a lot of patience and a lot of determination, I think it's pretty hard to be a scientist, because we work really hard to make really tiny baby steps.
Yeah, absolutely. I mean, it's a long-term commitment, right? So
it's a long-term commitment. Ulrich's back.
I'm back too.
Can people hear Ulrich?
Hello.
Okay, great. Yeah. Right.
Ulrich is also quite silent.
That's my natural disposition.
Ulrich, you want to take up some questions? Because
Let's see if there's anything not specific to distributions of spikes.
There's a question that's sort of philosophical about why do neurons have a refractory period? It's not philosophical. I think that's just a limitation of biology, right?
Yeah.
I would also say that it's the materials that we have been given to make a neuron.
Yeah.
Yeah.
There is a question about, like, what, presumably the actual value of the refractory period is subject to some evolutionary pressure. That there is some pressure to get it down to like 1 to 2 milliseconds, but faster than that, like the energy versus speed trade-off is not worth it or something. That's a hypothesis anyway.
So there's a fun question here about, is there a Y model that can explain the existence of the refractory period? So I'm gonna modify that a little bit and say, you know, is there kind of a normative explanation for why you'd actually want to have a refractory period? And I don't know if anyone's actually looked at that. I totally agree that, you know, refractory period is just a limitation of the actual material that you're working with, right? You know, that depending on what material you will have a different refractory period. But, you know, if anyone could come up with the good reasons for why it would actually be useful to have a refractory period, you know, that seems interesting, but I don't think anyone's actually looked into that.
Right.
But maybe refractory period doesn't have an explanation, but people do come up with explanations that why neurons have such extremely low firing rates in most part of the brain.
Yeah, no,
the argument is always about energy, right?
Yeah. Firing
so
actually.
do you guys believe that argument?
At a large population level, you could tag them together.
Do you guys believe the energy argument about spikes?
I don't.
What do you think is the constraint?
I mean, energy, of course, is a constraint, right? Of course, we can't heat up the brain so much that it just burns itself.
Right.
But I think having a powerful brain gives the organism much more advantage to harvest energy, that it can always compensate for that. To me, for the brain to be optimized, I think the better constraint is that it should reduce the variability in the output of the brain. It should be more and more precise. Right? If I'm a monkey trying to jump from one tree branch to another, I do want to catch it because there are fruits there. Right. It doesn't matter how much energy it takes. If I miss it, I'm done. But if I'm reliably doing it, even if it takes energy, I'm getting enough glucose.
Right. I mean, I think it depends a lot on your ecological niche, right? Like if you're a koala and you have no predators and all you do is like sit in a tree and chew on eucalyptus leaves, you don't have a lot of pressure to be fast or precise.
Oh yeah, fair enough. Then you have even that constraint is gone. Absolutely. Then you need humans to preserve you.
Now you do. Well, humans first to take away your, like,
Yeah.
and then other humans to push back.
But if we follow that argument, then there should be different ecological pressures for different animals towards have different trade-offs between position and, you know, metabolic, you know, restraints, right? So, you know, that's an actual empirical question you can then go out and look at. You can look at the firing rate of neurons in koalas versus firing rates of, I don't know, rats or, you know, whatever. I don't know what the right animal is to compare to, but yeah.
It's a great. Has anyone done neurophysiology in a koala?
Don't know.
They're too cute. They're too cute. You can't do it.
We don't like doing experiments on cute animals. That's true.
We do not.
But I mean, number of animals in neuroscience are decreasing, so that's also.
Yeah, true.
That's that's unfortunate.
All right. What other questions do we want to answer, guys? We're almost out of time. I can't believe it.
It's so much fun.
Yeah, this is fun.
I mean, just to go on this energy thing a little bit, like one of the things that I think is really missing from a lot of computational modeling, but also artificial intelligence work, is the energy constraint. Like brains formed with these constraints, like heat, energy, maybe speed, all these resource constraints. But usually when we model like networks of neurons, we don't think about the energy cost at all. We usually just assume that like there's enough energy and we don't have to worry about heat dissipation and we don't have to worry about building up of metabolites. And I just wonder like how much adding that stuff in can really help us think about cognition. What do you guys think?
I mean, there are areas where that is being taken into account, definitely, you know, in certain amounts of like reinforcement learning, for example, you know, it's a key constraint too, right? So that, you know, I agree, it's something that we can probably think of in more different types of diverse models. But there are, of course, areas where it is being taken into account, definitely.
So you mentioned RL. Can you flesh that out? Like, you mean this whole like the cost of planning kind of thing? Yeah,
I mean, you know, there's one of the interesting things about RL, of course, is that you can put in to your reward functions whatever you need, right? So, you know, if planning, for example, is something that's important, then you need to put that into it too. If just movement, for example, is important, you need to put that into it too. Yeah, I mean, you can load into your reward function whatever you think is the most relevant, and then you can go out and compare that to the behavior of an animal, for example.
That's true.
Can I pick on something you said? Which is that you can load into the agent whatever you think is most relevant, but then you are playing God, right? Like, shouldn't we kind of let the system figure it out on its own? Like, isn't this part of the I don't know, exploratory process?
Yeah, no, okay. So whenever we are modeling, of course,
then you put it in as a free parameter and you estimate how much the movements cost.
That's the thing. You can do meta learning too, right? And there's a lot of work being done right now on that too. Yeah. So that, you know, meta level where you actually have to learn the reward functions too. And there's some really cool stuff, of course, being done, especially related to kind of more AI side of things. Yeah. That really is kind of pushing those kind of ideas right now. So that's kind of one of the really interesting areas, actually.
Yeah, I agree. I think meta learning is really, and I think, I don't know if we're going to get into meta learning by the deep learning ends of the course. We might touch on it a little bit. I don't think we're doing meta learning, but yeah, I agree that that's one of the more interesting things. Like, if we just play God and we like implement the cost function that we think is the right one, then odds are we probably got something wrong. And so we should let the system kind of discover it on its own.
As modelers, we always make choices, right? We always have to make decisions about what do we actually think we want to learn. But it's really exciting if we actually find ways of letting the system learn about these things too, which is really what meta learning is about. Yeah.
So if you guys haven't heard of meta learning, all you guys out there, you can go check it out. There's a lot of, it's like a really hot topic right now. And I know hot topics are not like always the best ones, but it is kind of an interesting way to go. Think about letting the system teach you. Yeah.
I mean, the meta part is a bit funny. It's more just like, we decided reinforcement learning was one little thing, and then everything that's beyond that is meta.
There are all these different implementations of meta learning now, where it's like, oh, we have to then make choices about, is it the derivative of the weight update rule that is the thing that is the actual, like, needs to go into the cost function, and then we get into the second level of, like, making decisions and playing God.
Yeah.
Yeah. Oh, good. We've got some questions in the chat of what is meta learning. Oh, fun. Go look it up. It's like this whole, branch of machine learning that's really hot right now. And so if you want to go take a deep dive into a lot of math, you might discover something really interesting. Yeah. I think a one, you guys didn't answer this question, right? What do any of the models among, like, the how, what, why, and also maybe like Mars 3 levels answer the question of what the brain is actually doing? It's kind of a philosophical question. It can be a very concrete question, but it can also be kind of a philosophical question. It kind of leads from what we've been talking about, I think.
Megan, are they familiar with Mars level? Because I don't know if they
went over it very briefly today. Yeah. In the outro. Yeah. So in the outro we have, or they did like the what, how, why in the tutorials, and then we start to link them to Mars 3 levels. And so as a reminder, because I know it's fast, but we've got the computational, the algorithmic, and the implementation level, and they sometimes map onto the what, how, why, but sometimes not. And so do these Mars levels of analysis, or the what, how, why, do they answer the question of what the brain is actually doing? There's a very, like, concrete way of answering this question, and it's also a very, like, philosophical kind of heady question.
There's one question which I think one of you should take. I don't think I can say anything useful there. This was it's hanging for some time now. It says why we can use 5 to 15 intervals as representative sample based on the, let's say, interval time / total time equal to spikes in interval / total spikes in tutorial 1. If we need to do tests, the deviation or other statistical characteristics, but I think the question is about finite data.
Yeah, I mean, it's a good question. I think for the sake of the tutorial, it was just like a very basic check. Mm-hmm. It's more like if the percent of spikes in that window were very far off the overall duration, you would say it's definitely not representative. Like if the first 1% of the time contains 50% of the spikes, you would say this is not representative. But if it does match in percentage, it doesn't mean that it is representative. So how would you check? Probably KL divergence, I guess, on the ISIs or something, which is a statistical test of whether two distributions are the same. So you can look at the distribution, the first 5 to 15, 15 to 25, whatever. 5 to next 10 seconds, see if they're similar. Should we go back to the philosophy though? Of like,
like, are we actually learning anything about brains? That might be a good place to kind of wrap it up a little bit, because we're coming up on the hour here. We can end with a little philosophy. Everybody should study a little philosophy. That's my plug, by the way. Everybody should study a little philosophy. It makes you a better scientist.
I agree.
And always ask a question like this, which is like, are we actually studying the thing that we think that we're studying? Which is why I said, like,
isn't that the whole point of the NMA is to teach the kids how to, like, ask a question?
Yeah, exactly. Like, and ask whether the question that you think you're answering is the one that you're actually answering. Yep. So that's why I like this question, because, like, on the face of it, you can say, oh yeah, the implementation level, or the or in some ways the algorithmic level, or the how, of the what, how, why. These are, that's totally like a description of what the brain is doing. But there's a much deeper version of this question which is like, even if you can describe the biomechanics of the system, is that actually what the system is doing? Or is this still just a level of description that doesn't like get an explanation? So if you guys are interested in the philosophy side of this, there's actually in our professional development series, we've got a philosopher who's going to be joining us. And she's going to talk about representations and meaning, and whether the things that we think that we're studying are actually the things that we are studying and the questions that we are answering. So that's pretty cool. What do you guys think?
Can I add something to that?
Yeah.
So one thing we should always keep in mind, that when we have a physical phenomenon, when we create a model of it, we translate it into some other symbolic representation. And there we have some rules to manipulate those symbols. Like we take a biological neuron, convert it into differential equations. Now, it doesn't mean that whatever we have now created as a set of differential equation is the neuron. Differential equations themselves have their own properties, which may have nothing to do with the biology of the neurons. So we should always know this, that when you are studying the model and when you are studying the phenomenon. Yeah. Often this gets very confusing, that there are a lot of papers out where you wonder, like, is this something relevant to the question, or is it just a behavior of the model? So always ask yourself, like, what are you studying? Are you studying the model? Because if you are studying the model, then most likely you'll be studying applied math. You should be there. If you are asking a question about the brain, then of course it makes sense.
Unless, of course, you're trying to create some sort of like intelligent artificial system, in which case studying the model might be the thing that you actually care about doing.
Absolutely.
Oh, all conversations end with AI.
Okay, here also I want to say something. Okay, this has been bugging me for a long time. I think we should also not assume that the singular goal of computational neuroscience is to build artificially intelligent agents. Or this is not the goal of neuroscience even.
Oh, big question. You saved the big one for the end.
No, but I mean, this is one of the goals. Like, this is not the only goal. I mean, we still have brains, and we would like to understand it. This is such a fascinating natural object. So even if it doesn't lead to development of artificially intelligent agents, even then, I think just for the sake of knowledge, it's such a great endeavor.
But hold on, not just for the sake of knowledge, public health. There's all these diseases that we need to understand the brain, to understand depression and Alzheimer's and Parkinson's disease, all these things. So
yeah, the clinically relevant one got only a few votes here, actually. But I think clinical relevant
brain disease.
Well, when we voted on the goals at the very beginning.
Oh, clinically
relevant got, normative actually got almost no votes. So sorry for people who actually care about that.
Yeah.
But the clinically relevant one was not super popular.
I think it's partly like selection bias. Like, you go to Cosine or one of these computational neuroscience meetings, and you think like the people there are like the rock stars of neuroscience, but you forget that like neuroscience is this big and computational neuroscience is like this big in terms of funding. Like, most of the money is going to like drug addiction, stroke, epilepsy, aging, Alzheimer's, PTSD, basically clinical studies.
But the overlap is definitely there too, right? Like, computational psychiatry is a growing area, and there's a lot of really interesting stuff happening there too. Sean
Escola, one of our board members, is one at a pioneer in that field.
I think that's actually a big point of what coming out of NMA you could potentially do, is you could take the computational tools that you're learning here and take them into some of these other realms that are less computational and massive, and have these big, potential health impacts or big kind of societal impacts. And there's a lot of value that computational neuroscience, which Jeff, as you so poignantly put it, is this big in the neuroscience field. But there's a lot of power here, and I think that paying attention to beyond just the basic science, which is also a laudable goal in and of itself, like, comprehension and understanding and basic science knowledge as a society. Yeah. But if you can take it and go into computational psychiatry or, computational neurodegenerative disease studies, those kinds of things, like, do it. And
brain development. I mean,
Yeah.
brain development is really important for understanding things like autism and other developmental disorders, schizophrenia, and we definitely need more quantitative people working on those problems.
In fact, in development,
exactly. The point is that there are many avenues where you can take this knowledge of neuroscience, not just to make AI.
Yeah,
but
exactly.
you can make AI, right? Like, I mean, you can if you want to study if you want to build an agent that learns how to learn, that does meta learning well, what better system to study than like a 2-year-old and how the 2-year-old's brain learns? Because
they're kind of slow though. Like every day you could barely see any progress.
Do you have a 2-year-old at home?
8 months.
Oh, okay.
Wow.
Yeah. Well, but they're not that slow. I mean,
I'm just joking. It's pretty amazing.
It is pretty amazing, yeah.
Okay.
Yeah, computational psychiatry is something that I think is going to be growing also, and it's also something where it really is interesting because you actually learn a lot about a system when things start, quote unquote, breaking down, right? Like when things start becoming anormal, that's when you learn something about it. When your car suddenly has a weird sound coming from the engine, then that's when you actually start really figure something out about it, right? Like, so when things aren't working the way that quote unquote normally is, that's when you can really start learning something about the system.
Absolutely. I mean, optical illusions are a great non-disease example of that, right?
Yep.
That's my favorite way to introduce some of this stuff is like visual illusions. It's like these two things are actually the same size, but your brain says they're not.
Yep.
I like the checkerboard one.
Yeah.
The brightness, the shadow in the checkerboard. That's one of my favorites.
Yeah. My other favorite one, honestly, is the light from above prior, like where it looks like bumps and dimples.
Yep.
Because you expect light to come from the top, from above you.
Actually, the hollow face, right?
Yeah.
The hollow face one. That's so amazing. You
Really?
don't even know when you're correcting for it.
Yeah, if anyone has ever been to Disneyland here, like in the Haunted Mansion, you walk by all those faces and they look like they're watching you. All the like carvings. No? Really?
No.
Oh man. Okay. Well, maybe some people who are watching this have been, but they make use of this illusion to freak you out in the Haunted Mansion as you're like going towards the little cars because they're all concave and so they look like they're turning to follow you, even though as convex things. Even though really it's just a concave, cutout. It's pretty cool. All right, guys. Well, thanks. Yeah, sending the links. Perfect. Okay.
Actually, there's a great link about optical illusions. Give me a minute.
Send it. This is a good place to end, I think.
I sent one link, but it's not that good.
So this one, I know Michael very well. He was an optician in Freiburg, where I did my PhD, and he collected these illusions and explains them and breaks them. Right? There are these interactive graphics where you can break the illusion and see like where it's amazing what he has done for this.
What a great site.
Cool.
By the way, there's actually like an equivalent site at McGill for auditory illusions, where you like, depending on how close together information comes in the two ears, whether you hear it as two sounds or one sound. And it's like, it's pretty, I can't remember the guy's name. I could probably find it though. Auditory signals, exactly. I feel like somehow we're...
Ulrich, this is not your garage. This is your library.
Yeah, my
well, it used to be my garage, but nowadays then it's turned into my library.
That's the guy. What's his name again? Bergman?
Albert Bergman. Bregman.
Bregman.
Yeah.
Nice.
Yeah, I've actually been doing some of the modeling on that kind of stuff too. So that's why the book is, so close by.
Integration versus segregation. Yay.
Yeah.
That's so funny. I mentioned Gelman and there's two things and you're just like, oh yeah, I have the book here.
I do not have books like that handy. Not in my home office anyway, not right after I move.
Right.
Well,
my
guys.
real office is pretty empty right now because everything's been moved into the garage instead. So, yeah.
Okay, that's a wrap.
I think that's a wrap, guys. We went even over a little bit. We were having so much fun. So I think we should let these guys go. They've got some hubs to go to, some little virtual rooms to go wander around and hang out. And the last thing I'll say is if you guys are still here and you're still listening, please go do your reflection surveys. Please, please, please. That's really a big deal. It helps you. It helps us. And that's it for today for the main events of Neuromatch Academy. And we'll see you back here tomorrow. Okay. Bye, guys.
Thank you.
Bye.
Let me first welcome everyone. So welcome Europe, welcome Africa, and above all, welcome Iran. Isn't this cool? I couldn't believe it. Not all of you may have heard about it, but this night we get emergency permission to include all the Iranians for that. And I'm so excited. So, and people complain that no one is wearing hats. Hold on, I can fix that. 1 second.
What if we don't have hats?
How's this? Is this better? Yoo-hoo! Okay. Here we are. We aren't here for fun. Oh wow! Athena also has a hat. Look, we are all happy.
What I could do.
So, in any case, look. I guess you guys see that we're like extremely happy about what just happened this night. I didn't sleep much, so I will be a halfway brain dead moderator for you today, but you'll get over it. So let me first briefly introduce myself. My name is Konrad Kording. I'm professor at the University of Pennsylvania, and I'm interested in kind of machine learning and data about brains, and I'm one of the co-founders of Neuromatch Academy. And let me introduce the other discussions that we have here. The first person I want to introduce is Athena Akrami, who has an amazing lab at Sainsbury Wellcome College and University College London. Athena, do you want to say a few sentences?
Thank you, Konrad. Hi, everyone. Yes, I'm Athena, and we have a lab that works with maybe 3-4 different species: human, rat, mice, and synthetic models. So we treat the model as another species in the lab, and we are interested in decision making, inference, memory. And I'm so excited to be with you now and to be part of NMA. It's amazing. If I'm brain dead today, excuse me. I also didn't have much sleep last night, but we will be here for you.
Great, awesome. So the next person to join us here on the is Gunnar Blohm. So Gunnar Blohm is professor at Queen's University in Canada and has been a close friend and collaborator for many years, and was also one of the he was with the NMA right from the beginning. Gunnar, why don't you say a little bit?
Yeah, thank you, Konrad. I'm so excited that this is starting. We've been working very hard to make it happen, and this is like better than a birthday party, better than New Year's. It's like almost Christmas, but for like 3 weeks. It's amazing. So as a professor at Queen's University, my research is in sensory motor control. We're doing mostly human and artificial human, so models type stuff. And hopefully that'll come across a little bit over the next today and tomorrow.
Cool.
Oh, and I brought my Viking hairstyle as well.
It turns out that on the Slack that made NMA, Gunnar is called the Viking, and I hope by the end of NMA you'll get a feeling for why. But without further ado, well, it's the first day. It's okay if we spend like 5 minutes on introductions. I should say we will be joined by Arvind Kumar a little bit later, who I'll introduce when he comes on stage. But Crowdcast just gives us 4 screens, which I think is good. In any case, why don't we jump right in? So what we did today is we showed you 3 very different models on purpose. But we showed you 3 very different models and model classes that deal with the same kind of data. And we often do, or like we like to do that at the beginning of events, because it gets people to think about what it is that they really care about as neuroscientists. And so in that sense, I want to like briefly, there's 10 flavors to models. That at least, 12 flavors of models that we can discern. There's probably more, but there's at least 12. And we will ask you which of these 12, in a poll that I'll put live in a second, which of these 12 is most meaningful to you? And then we'll see how like the distribution of excitement about different model aspects it is. And the reason why this is important, let me be clear about that. If your goals are of a certain kind, and my goals are of a different one, I cannot meaningfully criticize your model with my goals, because your model has no reason to deliver on my goals. So you can say this is just philosophy, but in reality, it's not just philosophy. It is philosophy, and we need it to be able to do good neuroscience. And if we try and not do it, it just means that we do it badly. It doesn't. We cannot not do philosophy. We need to ask ourselves, what kind of models do I want? So let's go through that list, and that's from a paper together with Gunnar and Paul Schrader and Kendrick Kay. And so let's go through that list. So the first one is useful. I want to build models, and I want to build models that are of the nature that if I would implement them, they would solve real-world problems. The second one is normative, where I can say, I want my model to formalize what it would mean to work perfectly in, or like to work ideally in the real world for a problem that I believe that the brain actually has. And I should emphasize, Gunnar, Athena, if you want to interrupt me any point of time, and Athena, wave at me because I had to mute you because like you had like some sound, some white noise coming from your channel. The third one is clinically relevant. Like there's a lot of people who build models, and they want the models to be useful to improve lives of patients. There are people who build models with the goal of inspiring experiments. No, like you formulate things, and out of it, it is kind of a device that helps you come up with meaningful experiments. There's people who focus on microscopic realism. Does it have the microscopic properties of real neurons? Maybe. Does it have realistic physiology? Does it have like realistic synaptic learning rules? Things like that. Then there's macroscopic realism, which is, does it describe like the brain in terms of like the brain areas that are there, in terms of like the big scale connectivity maybe between different regions. There's behavioral realism, where I can say, well, does the model produce behavior that is like the real behavior? And like if I write a model of Konrad, does it talk like Konrad and make the same bad jokes? You can say, I might want models to be representational, which means that the units inside of the model should be in the same way as the units are that are within the brain. I might want my models to be compact, where I can say, I learn much more out of a model if I can write it in a very compact equation than if it kind of like has to be implemented over like 1,000 lines of Python code or something. We could, some people drive towards analytically tractable models. So the question there is, can I take a model and specify it in a way that I can use math to really understand it? And there's a lot of models of that kind. You can basically do it on paper. And for a lot of people, that produces a much deeper felt insight, and maybe a much deeper insight. So it's very dear to a lot of people. Then there's the idea of interpretable model. Can I take the model and kind of make sense out of it? And then there's maybe the most ephemeral property of models, which is like certain models are beautiful, no? Like they're symmetrically balanced. There's just something about like the way how they fit together that makes this be great. And so now I will put the poll live. So what I want all of you to do is go to the poll that I just put live and vote which of these is most important to you. And I want to make sure that you all vote. No, so just to be clear, there is down here on the screen, here, there's a button called polls. And I understand that some people will probably be using YouTube, and for people that have very weak internet, using the YouTube link is a very good idea. And let me share that here again. Here. YouTube link. For people who have very slow internet, you can go here, and it should considerably help. Downside, you can't chat with us here anymore. But now let's have a look at the poll. Now, I've never done that, but can someone tell me if the poll is now actually on screen?
Yep.
Awesome. Okay, cool. So let's see. Let's see how we are as a community about what we care about. Some people like useful models. I wonder how many of those people like.
I don't see the poll on the screen. I mean, but it's maybe just me.
It's at the bottom, next to the ask question and people.
Oh, but then it doesn't show up on screen. I made it like full screen, but apparently that doesn't work.
No, it doesn't show. Yeah, I mean, people should just yeah.
Okay, but you can all look at it. A lot of us wanted to inspire experiments. Quite a lot of people wanted to explain behavior. And then there's like a smattering about all the others. But like, here's why I think this is so important, that the bulk of the disagreement that I see between people isn't really disagreement in computational neuroscience. It's just that like Gunnar might be all gung-ho about representational, and maybe I really like useful models. And maybe Athena likes microscopic realism. And I don't say that this is exactly what they do like, but I just said that could be possible. And in that case, a disagreement between us might be completely pointless, because my model doesn't claim to have microscopic realism. And maybe Gunnar's model doesn't claim to actually solve the real world task. So then how can our two models really disagree with one another? No, we can learn from one another. But like this clarity about what we care about is really essential there. Okay, great. Yeah, Gunnar.
So there's a comment in the chat that it's unrealistic to just vote for one. Yes, so we force you here to vote for your favorite thing that you care about. But everyone has a different degree to which they care about all of those in a certain way, and that's very important to realize.
Yeah, and it can change across papers. Athena, sorry.
Yeah, I think I know. So I just wanted to emphasize on that if we change the poll to a kind of a ranked choice options, then it would have been maybe a richer picture, because I think like maybe a model that is useful at the same time, it might also be interpretable. It might also be beautiful, that they really overlap with each other. But each model might emphasize on one aspect more than the others. And another comment that I really kind of I would like to add a comment to what do we mean by useful, and what is a real world problem. I think like philosophy also deals with real world problem, and cosmology deals with real world problem, because they are just seeking knowledge, right? So if you really expand that, then I think a lot of models can be really useful, because they just like teach us about the universe around us, and that's very valuable in its own.
Awesome, cool. So we should go through the rest of the slide deck here, because we will now ask you to quickly give us a little bit of feedback. Why do we need that? Well, Gunnar, can you go to the next page? Exactly. So there's 2 pages. You either go to NMA Interactive if you're interactive, or NMA Observer if you're observer track. Why do we need that? Well, it turns out that there are things that I can copy. Like Gunnar teaches a course, I can try and teach a similar course. But NMA doesn't have like good role models that we could just try and copy. No, like it's a totally different scale. So that's why we really rely on your feedback. So we will now take 3 minutes to give you the chance to actually go through that. And I would like all of you to fill this out. It's every single person here should fill that out because it will help us be better. And it's the first day and we want to be there for you. And so please take and it's 9:20 now in Philadelphia. It's a very different time for most of you. And I'll wait until 9:23, as awkward as that might be. Three minutes is a long time if you have to quietly stare at the screen. So Tamara asks, but what if they haven't done the work project yet? Yes, most people shouldn't have done the work project yet. In which case, I hope that the questionnaire allows you to say not available or something. We will interpret it accordingly. It's the first day.
Yeah, even if you put in a random answer, we will know.
So Akhilesh is asking if we could play a fun song in the background. I didn't think about it. Does any of my co-panelists want to sing a little song for everyone? We have another minute of time. I guess there's no. Sarah says, please no. Yes, you don't want me to sing. Insert Viking music. Well, Viking music would be great. I think that would be very hilarious, but like this is the kind of stuff that like do a little singing that we might do a little later in the academy. Right now, we are still dealing with making sure that like our everything works. And maybe it's a good time for a few shout outs as well. The one person I particularly want to thank today is Patrick Minot, who is our tech lead, who has been doing absolutely unbelievably impossible things during the last few days, despite the fact that we continuously changed our opinions and
during the whole time.
Okay, cool. Why don't we keep going now? Gunnar, let's look at the next slide. Thanks everyone for filling this out. Okay. Neurostars. Gunnar, can you say something about Neurostars?
This is just to indicate again where you can find information, in particular for the interactive students here. So you all know that you have to go to the Neurostars main page, and then if you click in the black box, the Neuromatch Academy part, that's a private subsection. And in there, you essentially have a subsection, that's the first top arrow here, where you can find your particular information that you have access to, like your pods, etc. And in there, you will also have the links to the daily reflection that you just filled out.
Right. Okay, cool. Like that, that's the announcement for the Neurostars. Did we have one more slide, or was that the rest of the slides, Gunnar?
That's it.
That's it. Okay, awesome. Now we finally get to the good parts of that, which is the science. But before we do that, let's also bring Arvind on screen. here. Great. Okay, like it usually takes just a few seconds to get people on screen. Maybe we should already start with something that's been asked. Whose idea was the hats? So in neuroscience, it's a common saying that you're wearing a certain hat. No, like now I'm wearing my so-and-so hat. And the idea. Yeah. Hey, Arvind, 1 second. The idea that we'd be using the hats came out of the feeling that like day one kind of was lacking structure. So we brainstormed that a little bit. And then we came up with the idea of the hats to give it more structure. So, and I believe that I was the first person who proposed the hats.
I can confirm that.
Okay, great. So in any case, that way I also get to like show off my favorite hats. So thanks, Sophia, for your question. So Arvind. So Arvind Kumar is joining us from KTH in Sweden. Arvind, do you want to say like a few sentences?
Yeah, sure. Hi, I'm based in Stockholm at the KTH, Royal Institute of Technology. I was trained as an engineer, and then I switched to neuroscience. I kind of remember when Konrad was graduating, I was visiting INI around that time, and I was amused that a PhD student has a shoe on their desk, right? Coming from India, a shoe never touches anything academic. So I don't know if Konrad remembers that, but never. Anyway, I did my PhD in network dynamics. I was studying how neurons interact when they're connected as a network, and ever since I've stayed with that question. So my research in my group, what we are interested in is that how the connectivity and neuron properties, they interact to shape the network dynamics and hopefully also function.
Cool, great. So why don't we jump like straight into the questions? You did exactly what I wanted you to do, which is like vote on them. And so let's first talk about examples of hybrid models. This is a question by Kaysen, like hi Kaysen. Any example of a model that is not why, how, or what model, or any model that is a hybrid model. So there are certainly hybrid models. Do any of you guys want to like add one of them or like contribute a hybrid model? Gunnar, you've built hybrid models. Come on, tell us about it.
I mean, many models are inherently hybrid models, and very often whether you classify them as what, how, or why depends very much on your goals, actually. So you can even take, like, let's say, a Hodgkin and Huxley model, so single neuron spike dynamics model, and say, well, if I just want to fit my electrophysiological measurement of the actual spike and get the parameters out for each individual type of neurons that I've recorded from, that's a what model now, right? I've done nothing but like curve fitting. If I want to ask then, well, how is that happening, right? How are the different neurons different in terms of, maybe they have different channels, etc. Through the curve fitting exercise, then all of a sudden that becomes a how model, right? So we very often have these models that, depending on the question, depending on the interpretation of the model, can speak towards one or towards more than just one of the what, how, or why questions.
It's quite typical. Athena, do you want to share one?
Yeah, I mean, I think it's quite easy to, at least in the hybrid model, cover two out of these three. Like what usually is always part of the model, and then you try to kind of, out of the phenomenology, the curve fitting that you've done and the phenomenology that you've described, to kind of now link it to some mechanistic models or some normative model that would define, kind of explain the phenomenology. But recently there are also kind of attempts that like one model can have all three, right? Like if you want to get some sort of a normative model out of a neural network, right? Something that has that works based on some kind of a Bayesian statistics or probabilistic computation, and you want to have a kind of a neural network that implements that. So that's a how, and then the Bayesian framework is the why, and then they are going to explain bunch of phenomenon, either at the level of behavior or neural activity.
Yep. Cool. Arvind, do you want to share a model that is neither of the model classes?
It's very difficult, but I mean, I would even say that leaky integrate fire neuron is somewhere in between. It has a little bit of biophysical realism in the form of synaptic integration, but then we just say what in the form of just putting a hard threshold there.
Right. Yeah. No. Like, and I think this is important. These coarse ways of characterizing models, they do get at the heart of what drives us. They get the heart of why we do it. But every given project often has multiple of those components. It often has multiple of the what, how, why components, and it often has many of the 12 components that we discussed earlier. And I think that that's very important. So can
I add just one thing to that? I mean, it's also very important to kind of have a iteration between these three, because they add constraint to your models, right? So you might come up with some model that has explains some sort of optimal behavior, but then the question is that optimal with respect to what, right? We need to kind of operate in a I don't know, for example, in some evolutionary constraints or some kind of an environmental constraint of animal that would add a lot of constraints on your model, and they are really good, because then they are going to kind of link you to the mechanistic model and have a narrower classes of model that would explain better the system that you're dealing with.
Yeah. Oh, and to add another class, just talking about Paul Sisek, you can in principle build evolutionary models. Like they derive from none of them. They derive from yet a completely different logic. It's just like a lot of neuroscience papers are kind of close to these prototypical ones. So let's go through the questions a little bit. Is there a distribution that can have more entropy than the exponential distribution, which is a question by Yuki Fujishima. Arvind, do you want to answer that question?
Yes, of course. I think it's already in the tutorials, right? A uniform distribution would be one, for instance. But the question is not about just the shape of the distribution. I think exponential distribution emerges as a maximum entropy model when we put a constraint that we want a certain firing rate. Right? So the idea is that we want to put minimum information about which we are certain. So we say that I have a neuron which has a certain firing rate, and I don't want to make any further assumptions beyond that. And with this assumption, the model I end up with is an exponential distribution for interspike intervals. If you put extra constraints on it, then it may turn out to be a different shape, which will have a different maximum entropy.
Yeah, and in fact, in statistics, it's a whole branch where you take constraints and you derive what's the maximum entropy distribution for that set of constraints. In this case, we basically kept the mean number of spikes constant, but we could have kept then some of the squares of the spikes constant, and it would have led us to a different space. And there could be cases where we could make that point where we could say very high firing rate times are extra expensive because kind of the cell is outside of its normal range. And so yes, what's maximal entropy completely depends on the constraints you put in there.
One thing I want to add, Konrad, just to elaborate on it a bit, that when you say that I have, let's say, a lambda hertz firing rate, and if you assume that your intervals are equal, then you are making an extra assumption about interspike interval properties. When you say that it's Poisson, then you are saying that I do not know when the spike will occur. I do not know whether intervals are dependent on each other. But the moment you say that, is it regular firing rate, you have made an assumption about interspike intervals. So this is how you can further keep constraining.
That's right. Yeah. No, and I want to situate that a little bit. Reality is on neither of the extremes of that. We don't really have an exponential distribution because we have too few very short delay cases. We also never have a constant distribution because, well, until where? It would have to have a hard cutoff somewhere. And so reality lies somewhere in between, of course. So let's take a few more questions here. Here we have a question from Shweta Prasad, and already blanket apology. We have people from so many countries here that I will be screwing up your names like all the time, and please, like everyone already take my apology for that. But the question is, in tutorial 2, why do we draw current from a Poisson distribution? What's the intuition behind that? Arvind, should we start with you? I mean, like I
don't know which specific thing they are referring to. Is it like
okay. So hold on. I think I can take this. So the question is, in tutorial 2, we assume that the input neurons have Poisson output. Why do we assume that? The reason why we assume that is because when we look at neural data, in first order approximation, they generally look like they're Poisson. They aren't perfectly Poisson, so there's like some corrections that you could do that generally describe the data better. But it's generally the case that very few neurons in the brain go like click, 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 perfectly periodic. Yes, those neurons exist, but they're rare. And neither do they...
just the one thing that may help with that intuition is that when we look at the mean firing rate compared to the variance, they scale with each other, right? And that's very much Poisson.
That's right. It's one of the criteria or one of the properties that it often has. But it's also like it kind of implements that if I've seen the last interspike interval, like if I have waited for a certain period of time, the so-called hazard rate, the probability that now a new spike comes, is kind of constant in first order approximation, and that again produces like a Poisson distribution. And the details of that, we thought, in fact, at some point of time to build that into this day. It turns out that if you have an exponential interspike interval distribution, or like you have a process where it's basically the chance of each spike occurring in one interval is like fixed, then if you bin it, it has a Poisson distribution. It just means that the sum of Bernoulli distributions is Poisson, and this is beautiful, but like it just didn't really fit into the day. So, but that is like a super good and important question, and thanks, Shweta, for asking that here. Good. Next question. It's a question by Virginia Lee, and by the way, I want to add one thing. You guys are already answering the questions to one another. This is awesome. This is super cool. It's cool in multiple ways. Some questions will not be asked, and it's then nice if people have the answer. The second one is you get us an idea of what you're thinking about, and also it's like that's how a community is. Like we help one another, we explain one another things. So why do we compute entropy to compare models? Who wants to take that question? Gunnar, do you want to take it? Or Arvind, do you want to take it?
Yeah, I don't know if I'll be able to answer it, but since we were all quiet. First of all, this is not the only parameter or only measure by which we compare models. You could have compared it for some other properties. In this case, if we go through this why, what, and how, in this case, this turns out to be a why criteria that we have imposed that given a particular kind of spike patterns, what can I encode in this neuron? And that's why we are using entropy to compare. But it could be something else as well. We could have said that how many parameters are there in my model?
But hold on, there's two ways of interpreting the question, and I'm not sure how the question was meant. So in tutorial 2, we compared the entropy across different distributions. But there's also a case where we use entropy to compare how good models are, where you could say, what does it mean that my model is good? Well, it means that I need little extra information to know what's going on. Basically, I already have a lot of information about what will be going on. So in that sense, we use, and if that is what's meant, we use entropy to compare models because it basically is one way of counting how good a model is. A model that describes most of the data and why we therefore have low entropy in the residual is a better model than a model that explains little of the data. So I'm not sure how it was meant, but I think however it was meant, you should we hopefully covered it. So thank you. That was a great question. So here the next question is a question by Arif. And he says, I just want to, and here I at least know who to ask. I just want to know how Gunnar concluded in the intro video that from histogram of interspike intervals, including the after hyperpolarizations, neurons don't have a projection onto themselves.
Okay, so the idea here is that, so you hopefully all know that a Poisson process is independent of history, right? So if you have a process that's independent of history, that means essentially that the previous spike pattern, the previous spiking of the same neuron, does not affect the future spike pattern. Now imagine that you had a feedback loop, right? In that feedback loop, if a neuron fires, the feedback loop would essentially make it more likely to fire again because it projects onto itself. And that means that you introduce a history component here. And in the history component, if you put that to the extreme, you essentially break down the Poisson property altogether. So this is how we can, one way how we can know.
But Gunnar, let me just say, they don't need to know at this point of time of their course that a Poisson process has no memory. But it turns out that, like, if you have a random process that spits out basically how many spikes you get within, say, each binning window, like, by virtue of us saying, like, it's drawn from a Poisson in independent Poisson distribution, we kind of mean that there's no history dependence. But I think it's important. Like, no, we haven't covered that yet. By the end of the school, you may have seen that. But yeah, memorylessness. That's right.
Maybe that grants like a comment overall. So learning is an iterative process, and we have to start somewhere, and you will see things that might not immediately make sense. But we have tried to really integrate the curriculum of all of Neuromatch Academy in the way that ultimately, hopefully, this will all make much more sense. So I really apologize if some of the concepts we have skipped over maybe a little too fast.
Cool, great. So let's take a question by Nihal Tukaram next. There were some neurons which did not follow an exponential-like interspike interval distribution. Why is this so? Which is a great question, because reality doesn't ever in neuroscience conform all that well to the models that we have in neuroscience. With all due respect to our models, I don't want to diss our models at all. There's a huge distribution. Why is that the case? Well, we don't know. It could be that some neurons have balanced excitation and inhibition, short integration time scales, and therefore they approximate exponential better than others. It could be because neurons have different roles. Imagine I have a neuron that counts to 100 and then tells me that a second elapsed. That neuron, I don't want it to be very exponential. I want it to go like clockwork, click, 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 click. And there are cases where, say, a neuron, where you have these pacemakers where I have a neuron that bursts and then the next neuron and the next neuron, and it's a little bit like an avalanche or something, or like a ring going through it. And in that case, the role of the neuron is very different. It's not meant to transmit, say, information. It's meant to basically say it's 10 minutes past 2. And if you have such neurons, then they don't need to have the statistics for which we optimized here. So you can say there's a why reason for it. There's also a how reason for that. And there's probably many more reasons for that. And this is why it's so important for you to actually look at real data. So real data doesn't generally look like the textbook examples. And you just need to know that. It's shocking once you start really getting your hands dirty with real data that yes, there's on every axis I can possibly think of, you have these weird outlier neurons. And then there's usually general trends, but there's these outliers. Do you guys want to add anything to that? Yeah.
Yeah. So, I mean, of course, this is, as Konrad said, this is an idealization of what we expect for neurons to behave. Like Poisson is an idealization, and you will never fit something. But an important but subtle aspect of models is that they not only give us a comprehensive and compressed view of reality, but they also become a measurement. For instance, in this case, the Poisson distribution, you can use it as a measuring scale to compare different neurons. Like, how much do you deviate from the Poisson assumption? There are many reasons why this deviation may come from. And you can then search for how much it deviates and where it might come from. So we should also accept models as measuring tapes.
Right. Cool. Okay, let me. I apologize. I really need to take the next question, because this is a question by Tanya Rubinstein, who asked, Mighty A urged me to pass this pondering on to you. In biology, it's quite pragmatic to ask or claim to know why something is happening. Thoughts. So let me first tell you why I think a lot about the why. And I need to do this in the context of Horace Barlow's work. So Horace Barlow was one of the giants who started this way of thinking. He died 3 days ago.
Ooh.
He was just an unbelievable thinker. And my PhD thesis started with a quote from Horace Barlow's paper, which said, "The bird's wing accelerates downwards the air flowing past it, producing an upward force that sustains the weight of the bird." What would be an equivalent description of a sensory relay, how he called it? It means a sensory neuron in modern parlance. Now, why is this deep? Why is this so important in my view? Like, if we don't think about what the goal is of a system, it's almost impossible to think about it. And like, if you didn't know that birds fly, how would you understand their wings? It's extremely difficult. Now, the question is, how do we know that and what the why is? Like, we don't know that the bird's wing has the goal of producing that. The reason why we are pretty sure these days is because we did a lot of experiments and found that birds without wings can't fly, and like that we can do modifications, and we learned about aerodynamics and so on and so forth. But it's basically to understand systems where we don't understand their purpose, and like purpose is a correct word in terms of biology. There is evolution that solve certain problems for animals, like we have a beak, or like birds have a beak because, well, there's this stuff living underground that you can pick out of the ground that like you can eat if you're a bird. So this way of asking about what the why is, I think is an essential component of trying to understand a system. And sorry for taking so long, but like I needed to talk about Horace Barlow. And he brought this view into the field in so many different ways. So who of you wants to add something? Gunnar?
Yeah, so maybe just to add that it's really, and again, this is something we will hopefully emphasize more over the day tomorrow. It's really about diversity. Different types of questions can give us different types of answers. And any model is an abstraction. Any model is just part of the reality. If it was the entire reality, then it wouldn't be called a model, it would be called reality, right? So it's very important to sort of realize the fact that, yes, why questions are probably the hardest ones to ask. They're probably very, very gross approximations of reality. So very strong, very Sorry, I'm blanking on the word here. That's ridiculous. Anyways, so you got me. But the important part is that we can still learn something from them. And since they're hard questions, they typically provide profound answers. And that's what we're after as scientists, right? The word I was looking for was abstraction, which I don't even know why that popped out of my head. So why models are typically highly abstracted models. And so they're in that sense relatively far from reality, but it doesn't mean we can't learn anything from them.
Athena.
Sorry. Oh, sorry.
I'm sorry. You're good now. You're good now.
You are the master. I was trying to control it, but you.
I was unmuting you at the same time as you were unmuting you. And
I just wanted to mention one more example that can be maybe kind of illuminating here, which is the work of Donald Hebb, what we learned from him. So Donald Hebb was a psychologist, and he cared about organization of behavior, and he really wanted to his goal was to explain behavior somehow, right? Really ask a why question. Why our brain should work in a certain way in order to produce a behavior. But he gave us a very, very important insight about neurons that fire together, they wire together. And this concept of kind of wiring and synapse before any of us, biology, knew about the synapse. So it's very important to sometimes these really why questions that may sound very abstract and kind of far-fetched, they can give us really good intuition in order to look more carefully into biology and understand the system better.
Great. So let's go to the next question. Let me first control the videos here. So the next question. And I should say I moved one question, I removed one question here. I will sometimes do that if a question is better asked on another day. This was actually a great question. It's just we're a little bit more at local here. So this is a question by Liujun Li, who asked, why does firing rate increase when better? The voltage leaking speed increases. So that question, I think, has Arvind's name all over it. Is that right?
So beta is something that you're fitting to the model, isn't it?
Okay, yes. So it's the decay rate. Now we have a leaky integrate and fire neuron, and there are domains where making the neuron more leaky actually makes it spike faster, I believe. And I think that's at least the question. It sounds like it's an empirical finding.
I think the answer, you should ask yourself, what is happening to this neuron? How is leak related to what we call as the time constant of the neuron? So if neuron's time constant increases or decreases, its integration speed increases or decreases, meaning how fast it hits the threshold, that changes. So that's one relation, but this should not be always the case, because once you have increased the leak, you also have reduced the effect of the inputs, because the membrane can't hold that much charge. So this is like a double thing, that on one hand, by changing leak, you are making your neuron faster, but at the same time, you are reducing the effective weight. So in this case, most likely what you are doing is that when you are increasing the leak, you perhaps needed more input to this neuron, and when you added sufficient amount of input, it definitely spikes faster.
Right, but let me see if I get the intuition right. So if I have a long time constant, it means that if I was unlucky enough to get negative current, I will basically be very strongly hyperpolarized. I will be very far away from the spiking threshold. And I can spend potentially a long period of time bouncing around there. And so in that case, the leakage kind of gets me towards zero, which gives me yet another chance to reach the threshold at the next time step. So I think something like that is the intuition there.
Yeah, that by leak kind of gives you a lower bound, right, below which you will not go.
That's right. Yes. Yeah. It will exactly. It will bound that. Now I wonder what the dependency is and how to understand it. This is probably something that the field understands well, Gunnar.
Yeah, so one way to think about it is to take it to the extreme, where, say, if you have 100% leak, essentially, but then a single incoming spike, essentially, can trigger the neuron, right? Then essentially you would spike every time a excitatory spike happens in the input, right? But now if you include essentially memory into the membrane, right, by not having as much leakage, or maybe having no leakage at all, then you're averaging of everything that comes in. And if everything that comes in is balanced, excitatory and inhibitory, you're averaging across that all along. So it's much, much harder to reach the threshold in that situation. So those would be the two really hard extremes on both sides.
Yep. Great. Let's get to the next question. We will not get through the questions, just to be clear here. But this is a great question. And I love how the voting on questions really makes sure that there's lots of really, really interesting questions. It's really great. So let's see. So this is a question by Samuel Picard, who asks, why do we use Shannon entropy and not some other formal definition of entropy? Who wants to answer this? Because, okay, let me admit I'm a little clueless here. I do know that there's a set of definitions of entropy, but there's certain axioms under which there's only one. I must say I don't know. It seems like the right solution to the problem. See, here you see, we aren't quite sure either. You can, under certain assumptions that seem desirable, entropy is the right measure of information. Okay, look, we will just simply skip that question because we don't know the answer to that, and that's okay. And I think this is something that is really important for you all to see. We don't have all the answers, and no single person in neuroscience has all of them. And there's always, yeah.
This might be a question, though, that might need a little bit more specification. So there might be another day where this question could come up again, and it might make more sense on that day. So just maybe keep it in the back of your mind.
Cool. Okay, here's a question by Pui Shi Li. Are there any statistical methods that we can systematically evaluate how well our decided distribution, exponential in this case, fit the distribution of real data? Oh, this is great. Who wants to answer this question?
Gunnar is smiling.
Sure, I can answer. I mean, the short answer is yes, of course, and you will learn all about that on day 3. Essentially, all that day 3 is about model fitting and how to evaluate how well your model actually fits. And yes, there's many different statistical methods you can use. There's also other methods you can use to evaluate whether your model is good and a good fit. That depends on your own criteria. So some people might be interested in, for example, qualitatively describing certain things, but I don't really care about quantitativeness, right? So one of the criteria that you voted on earlier was simplicity or elegance, right? So very often, as a physicist, I'm a trained physicist, I would prefer a model that has very few parameters and ideally can be written as a one-liner in terms of equations, right? Now, that might do a terrible job in terms of fitting the exact details of a complicated system, but it might give me a very elegant description of the sort of overall rough behavior of the system that I'm very happy about, right? So here's a criteria where, if you fit a deep neural network to your data, that might do very, very, very much better than my simple one-liner, right? But I would still prefer my one-liner because I can learn much more from that one-liner than from a deep neural network. So there's both statistical methods for evaluating, an R-square or whatever it is, but there's also other methods for evaluating how good a model actually is. And it's very important to keep them in balance. And when you set out to model, and you will see that tomorrow, it's very good to from the start, define what your goal is, what you will ultimately really want to care about.
Yeah, But maybe to add a tiny bit to that, because I think the question was kind of fishing for that. So one thing we often use to say how similar to probability distribution size, we use the KL divergence, which basically says how surprising is the data of one process under the assumption that the other process describes the data. That's one of the terms that might help you if you want to already dig in. But it's right, we will get extensively to it later in the academy. Now I should say it is 10 on my time zone. It's much later on your time zone. Officially, this is over. I will, if that's fine with my co-hosts, I will keep taking a few more questions. But you're all free to go, and if there's project work for you, please don't be late for that. If someone is expecting you, don't be late for that. If your family has dinner ready, please don't be late for that. But we'll take a few more questions if that's fine. So here we have a question of Patricia Rubish. Is there a good example? Oh, hold on. Is there a good example which primarily has beauty as an objective? Isn't it more an emergent property of the process of building the model? Does anyone have a good example of something that's super beautiful?
Super beautiful. I mean, it really depends on what's your definition of beauty. In math, what I learned, what beauty is to bring together something completely unexpected, like the famous Euler equation, right? It brings together exponential pi, imaginary iota, and 1 and 0, and so on. So that's beautiful. I don't know if in neuroscience we can say something like that we have reached this level of beauty. In a way, if you think about McCulloch-Pitts, I think that's an awesome model, right, in terms of beauty. It is so simple, and it has so many nice properties. And if you stretch it, I think you can really bring it back to biology as well. So to me, the very first model in neuroscience, or maybe second model, I would say, is by McCulloch and Pitts. And this ANN is, I think, super beautiful. Other beautiful model is Lapic's description of a neuron. Lapic in 1907 proposed the first model. At that time, we didn't even know what is happening in the neuron. And he just said, yeah, just assume it to be an integrate fire neuron. That's it. So to me, in this case, simplicity is beauty, and reducing this amazing complexity of biology to simple math of either a threshold or additions and a step function. I would say that's beautiful.
Yeah. Do either of you want to contribute an extra model for what you find beautiful?
Sorry.
Okay, Athena, do you have a beautiful model?
No, I think I totally agreed with Arvind that it really depends how you define beauty. But if you define it based on maybe simplicity, kind of something that works based on Occam's razor, the minimal model that would explain the most things. I don't know, maybe again, going back to Hebb, I really like the Hebbian theory. And a lot of, it explains a lot of things that happen in the brain. It is producing a lot of artificial intelligence, even to this point. And it's really simple. So I think that might be a good example. There are anti-Hebbian plasticity rules as well that and it's not the ground. It's not the only truth, but I think it's very powerful and simple.
Or what about Lyapunov functions for learning, for the dynamics of learning systems? There's a lot of different, incredibly beautiful models whose usefulness hasn't been proven yet. But they're great for me.
It's very, very useful for any nonlinear system. That's an awesome idea, right?
Yeah. Do you want to explain what that is? Arvind, do you briefly want to summarize it for our audience?
So the idea of Lyapunov function, so basically we struggle with calculating stability of nonlinear differential equations. And Lyapunov, I think, I'm now over-interpreting, but I think he had this deep insight that if we relate now math to physical systems, that in a physical system, stability means finite response for finite inputs. And how do you reach there? And there he said that let's define something energy equivalent for our system of differential equations. And then you just relate it to the physical analogy of energy, that for a stable system, energy must go down. Yeah, and there comes out this idea that your Lyapunov function should be positive semi-definite for a stable system. And as long as you can define it, you have the stability notion. This is beautiful. And you should also appreciate that we are just there where Lyapunov left us. There's hardly any conceptual progress on this.
Yeah, isn't that interesting? But it's for people that read that like literature a lot, Lyapunov functions are just like so incredibly beautiful. It's just like in a way it allows you to like look at a system and very easily make very strong statements. And it's if it's useful or not, I don't know, but it's just beautiful. So let's keep going here. We have a question by Duygu Ozbakci, who asks, what about falsifiability? Aren't the good models need to be falsifiable?
Can I comment on that?
Yes, of course.
I mean, I think if they are not falsifiable, we should not even discuss them. So that's of course, I think falsifiability is really, really important. And maybe the very first criteria about one of the first criteria about taking any model seriously is if they are falsifiable. If they are not, I really don't know what's the point about having them or discussing them, right? And it's always a scientific practice is about having multiple hypotheses at the same time in front of you, and multiple models that would just rule out your hypothesis more than proving hypothesis. I think that's maybe more difficult and more important if you want to make some scientific progress, is to falsify models and falsify hypotheses and propose new models and try to falsify them.
Great question.
Slightly. Oh yeah, go ahead, Arvind.
No, I just wanted to remind that there is some interesting chat going on, and they're asking are Bayesian models falsifiable?
Okay, that sounds like Gunnar. Do you want to answer it, or should I? It's kind of.
So let me give like a very brief sort of so there's different types of models, and the free energy principle came up, which is more of a framework and a set of tools than an actual model per se. So we have to be careful here in really when we think about models in really asking what is a model exactly. The free energy principle is really a set of tools borrowed from physics that allow us to build models ultimately, but itself is not a model. And if you ask Carl Friston about that, he would totally agree with this.
Yeah, Bayesian is not a model. Bayesian is a framework. It's a clear subset of Y models. And every individual Bayesian model is refutable like any other model. Now, like if I say this is the predictor for what you'll do in a certain situation, you do experiments, you show that it's not, and it's refutable. The framework isn't, and it would be insane if the framework was refutable. No, like what is Bayes? Bayes is like, we'll get at it like in exactly 1 week from today. But Bayes just means that you use uncertainty in a good way. Like, how could that possibly be refutable? That doesn't even make sense to have that be refutable. Now, is it the idea that you always use all information optimally? Yeah, sure, that's refutable and it's wrong. But like that question, is Bayes refutable? That's like saying, is the idea that the brain is that the brain computes by lots of neurons that interact, is that refutable? Like, no, it's like a truism in the same way as like the fact that you need to deal with uncertainty in the real world is also a truism. Like, it can't be refuted because it's obviously true at some level. And at the same time, every individual specification of it can totally be wrong. Like in the same way as a How model can be wrong. Like if you say we have excited to balance excitation and inhibition, explains all kinds of data. And I'm like, okay, I'm going to stick electrodes in and see how much excitation and inhibition. Look, they're not balanced. Then I refuted it. And in the same way, if you sort of like have a Bayesian model that says the stuff that you see is more important than the stuff that you hear if what you hear is very noisy, then yes, I can refute that by doing that experiments and seeing that it's not. So
maybe the analogy would be to say something like, oh, is linear systems refusable or linear algebra refusable? Oh, no, it's not. You can't falsify that. That's just a set of tools that exist independent of what you apply them to. Now, if you build like a linear system model of the brain, is that refutable? Oh, yeah, absolutely it is. It might be a very bad description of the brain.
So Gunnar, the next question is like decisively for you because Matteo Mancini asks if you can please wear your favorite hat.
It's not my favorite hat, but I wore it at the beginning. So here it is again. This is my outdoor hat when I go hiking in the Canadian bush.
In the NeuroMatch Academy logo now. It
has to have a NeuroMatch Academy logo now.
So I think this is as far as we can go in that session. I ran a poll to see what people think, and we are basically split half and half into people who want to like break off right now or very soon, and people who want to basically keep going forever. I personally could go forever, and well, we might find a time at some point of time to like open-endedly discuss. But let's thank our panelists again. Thank you, Arvind. Thank you, Athena. Thank you, Gunnar. And let's thank all our participants. And like this fact that you ask those questions and comment on them and like have this debate with us, this is like incredibly valuable. So thank you very much and enjoy the rest of NeuroMatch Academy.
To be here and talk about models with you guys. And I'm also really sad, by the way, that the big hat and the black and white striped hat are not winning at all. So I'm kind of upset, and I'm wondering whether maybe I should switch to the hat.
No, I think we should ignore public opinion.
Fair enough.
Take it or leave it. I'll be wearing my big hat. That's how we roll here. Now it's now after the introductions, let's jump right back in. And maybe let me briefly say why I think this is so important. So we do neuroscience. When we do neuroscience, we cannot avoid but make philosophical statements because in a way we decide which models we like and which models we don't like. And that difference ultimately is about like what we think is important. And what we think is important is not something that we can read up on something. That's something that we need to make our own decisions. And that's why I think it's so important that we think about the philosophical and the value. So let's briefly review the 12 points that we've been talking about here. So there's useful, and there will be a poll. And I will not open the poll until we went through all of them, because otherwise the first one will just totally win. So let's go through those 12 points. The first one is some people like useful models. What that means is like models that if we implement them can actually solve real world problems. And you can say, that's awesome, because if they can implement real world problems, then we can use them for something. And that's why it's nice to have models that are useful. The second one is normative models, where we can say, does the solution that we find in the brain or in behavior, is this the optimal solution to like a problem that really exists in the outside world? So that's different from useful. In the second case, we want to ask to which level is the brain the optimal solution to a generic problem in the outside world. There's some of us that really care about clinically relevant models. Can a model help us produce the insights to develop or maybe evaluate clinical interventions? There's people who like models to inspire experiments. Like we go through the model, we build it, it has various components, we can see what happens if we mess with stuff, and then we can see if that inspires us to do experiments that mess with stuff and see and have things that we can compare. There are people that are really interested in microscopic realism. What does that mean? You can say, I measure tuning curves. I want to ask, are the tuning curves actually similar between my model and reality? Maybe are the synaptic learning rules the same as them? There's people that are interested in macroscopic realism. Maybe is the average activity in some brain area the same as the average activity somewhere in my model? There are people who are interested in behavioral realism. Does the model faithfully describe the behavioral data that we obtain? There are people who are into representational ideas. Is it that the representation, is it that what the neurons jointly encode, is that the same between the two, between the model and reality? There are people who like compact models, where you could say, if a model is short, then I can write it and I can understand it because it's so small. And that's why it's good to have models that are compact. Maybe if I like that, I would be willing to trade that off against something else. What if I have a very small equation that describes most of the behavior, and I could have a much longer equation that describes a little more of behavior, but I want compact equations? There's people that like analytically tractable models. There's a lot of people who gain a lot of insights by trying to understand, basically have equations that they can solve with pencil and paper, and that like provides an insight to them that they can't have otherwise. There are people who want interpretable models, models that they can kind of like put into context of biology. And then there's people who just really like beautiful models. Now, beauty is in the eye of the beholder, of course, but there are a lot of models that a lot of people in our community agree that these are just incredibly beautiful models. And there is something that makes them resonate with the way we are. So these are the 12 types, and let's like immediately put that poll on. And here's the poll for all of you. Now I want all of you, every single person who's in the audience, to go to the polls and vote for the one of the 12 criteria that is most important for you. And to already preempt a question that you will undoubtedly ask. Is it that every person or every paper can have only one of them? No. Of course, a lot of papers combine multiple such criteria. But it's important for us to be aware of what they are. And in reality, if you concentrate on all of them, you will probably produce models that are very hard to make sense of because they kind of appeal to everything. Now, these criteria lead to a lot of problems in the neuroscience community because people dislike one another's models. And in possibly the majority of cases, it's not about, say, the mathematics being wrong or like it not describing a lot of data. It's really just about that maybe I like models that are representational and maybe Kate likes models that are normative. And I'll be like, but Kate, your model is useless. It doesn't describe representations. And Kate will be like, but Konrad, I will have to reject your paper because it doesn't lead to any insights about why the brain is the way it is. And to avoid this kind of like useless disagreement, we need to be aware of what the claims are that we make in a paper. So why don't we see how things are? Wow, this is beautiful. Like it's very distributed here. There's a lot of people in this session that are into behavioral realism. This is interesting. The Europeans were considerably more into usefulness. I wonder where that difference is coming from. Megan, what was it in Asia? Was there anything that clearly differed?
I think it was last night, so I don't remember exactly. It was late last night. But
what you guys don't know is that that all of us have been sleeping a very limited amount recently.
Yeah, so last night was a little bit of a late night, so I don't really remember, but I do remember this. So clinically relevant was like microscopic before, and now it's actually a pretty hefty amount. So I think that that's kind of interesting too. And so that we can talk about, why clinically relevant might be like more or less useful. And I think people might have changed their mind by the time we got to the end of the talk there, but I thought that was kind of an interesting thing. I think useful also was kind of winning. Maybe we can go back and look. I should have taken a picture. It just wasn't going to happen last night.
Yeah, but Megan, the data is there, and in fact, for everyone, we will have at least on our side, we get the logs of what everyone plays, and maybe we can even do something useful with it. Okay,
yeah, we should go look.
we have a lot of slides to get through, and then we have a lot of questions to get through. So let's jump right in. Let's look at the next page, Megan.
Well, so first there's this, which is the happened in the poll that you guys actually ran. And so useful is kind of winning here. Clinical is like not winning really at all. Interpretation, look at the difference between interpretation for our group. Interpretation was like barely in there, and interpretation here is like really very big. It's like the biggest one actually. So that's kind of interesting. Yeah. Huh. All right. Well, but this just shows you, right, that everybody's ideas are different about what they think is the right goal, and that's okay. So this is the next thing that we need to do, though, right?
Great. Exactly. So, Megan, do you want to introduce the reflection slide, or should I?
Whichever. You can do it if you want.
Okay, cool. As I'm the host, I guess I should be doing it. So, NeoMatch Academy is in a unique situation. There is no other summer school like NeoMatch Academy. You know, like if you run like a small course in an area where others run courses already, you can just focus on implementing or copying the courses that work well. NeoMatch Academy doesn't really have courses that we can meaningfully copy. So that is why this is so important. And this is why we will ask you to do this right now. So please go to these web pages. If someone could like copy and paste those links into it, that would be fantastic. But basically, let's see. I'm sure someone will find them. These are questionnaires, and they basically give us the feedback that we need to make this be maximally useful. And in fact, we will try to be reactive even during NeoMatch Academy to keep making it better as we keep going. And so you saw here we have like exactly, yeah, there we have the two of them. So if you're interactive, go to the interactive one. If you're observer, go to the observer one that we have there. And I will be quiet here for 3 minutes, or I'll just be chit-chatting to give you the chance to do this right now. And so please do us the favor and go there right now.
Can I add one thing too? That like this reflection process isn't just for us, it's also for you guys. It's like to think about what's working, what's not working for you, and like where you came into today, which is just day one, and where you left today, just day one. But we're going to try to do this every day. And so this will kind of help you think about where you're coming from and what the stuff that you learned today and the stuff that you went over, like how that's actually applicable to the work that you want to be doing in the future. So it's not just for us, it is for you guys too. So please do this. Take it seriously. Thanks.
Right. And I want to, yeah.
Oh, good question. Who is a mentor for the questionnaire? So you guys haven't been assigned mentors yet, to my knowledge, right? So you can probably just put, not applicable.
Not applicable, yeah.
Yes, that's correct.
And same thing. I think there's a project question, and that also should not be applicable so far.
Yeah, but you'll get there.
Let me say one more thing about the question. So what's going on here is already perfect. So I see a lot of you are asking questions, and a lot of you are answering questions already. It really helps to understand things, to answer other people's questions. The thing is also, we would love to answer everyone's questions. But for a lot of the Q&A sessions, we will just not get through them, because like as we discuss questions, you will have new questions. And there's a lot of people in the audience, which means we will not be getting to all questions in most cases. So in that sense, it's great that you already try and like answer one another's questions. And we're super thankful for people who make sure that like all questions get answered. And I'm sorry about that, but like, what can I say? We can't get through all of them. At least in the Europe one, there was no way of getting through it. Okay, so let's give them another minute. Oh yeah, and talking about chit-chat, like those mascots, like I can see them on Neurostars, and oh my god, this is just so cool. It's like we're a community, and it's important to have like a culture in a community. And here come the koalas. Great. So, and I should say one thing. It sometimes happens that people lose sound on podcasts. Reboot your browser. It happens that you have a low-speed internet, in which case, see our YouTube stream, which requires less bandwidth. And if for some reason sound stops, reboot your browser. If you have horrible sound quality, make sure you don't have 2 tabs in which Neuromatch Academy is running. It has happened to me multiple times, and it's always a little embarrassing. Great. Okay, I think we gave everyone time to answer it. Megan, is there another slide after this? This is the last slide.
No, that's it. It's just a reminder that if you would like to find these links later and you've closed this chat, you can always find these in NeuroStars as well. So you've got, if you go to either the interactive students or the observer students category, then there's a daily student reflection link and information. And so you can always find this link there. But please don't fill it out until you've gone through the whole day, because then it's kind of like, what's the point? Thanks, guys.
Great. And so here we are also joined by Gunnar Blohm, who on Slack is called The Viking and has been doing all kinds of things for Neuromatch Academy. Gunnar, why don't you briefly introduce yourself?
Thank you, Konrad. So as you know, I'm at Queen's University, and I'm generally interested in sensory motor control kind of questions. Anything sort of from decision-making, working memory, to planning and actual control of movements of pretty much anywhere in the body, mostly eyes and arms though. So I don't want to say much more about me, because you can look me up anytime. I brought my Viking hairstyle just to prove that I'm actually sort of Viking, instead of the hat. But if you want me to wear a hat, I can also wear a hat.
I think there will be a majority opinion that wants a Viking hat. I've got to admit that.
Yeah, I don't have a Viking hat here. Sorry, Vikings actually it's a myth that Vikings wore
Coordinated.
It's actually wrong. Vikings do not wear the horns hats. It's out of the movies. It's not real. They did not wear hats. Or
but you could wear a hat, in which case Vikings would wear hats.
I could wear a hat. This is my Canadian outdoors hat. I can wear that. But I think it's much better without.
Okay, great. So why don't we jump right back into the question? So the first question is a question by Virginia Lee, who asks, why do we use entropy to compare models? Why choose Shannon entropy? Could anyone explain information theory a bit? Do any of you want to take it? Should I take it?
I just want to say briefly, I won't actually answer the question. I just want to say briefly that you will learn about information theory in week 2. So I think it's a little too early to really go into the depth of that. But maybe Konrad can say a quick word about why we use it for comparing models.
Yeah, so there's multiple levels for this question, and I'm not 100% sure which one is meant. So the first one is we use for tutorial 2. We use this to compare, say, exponential versus like just a single peak versus double peak and things like that. Why do we do that? We do that because the way we formalize the normative model has the structure that we say there is a constraint. Maybe the number of spikes is fixed. And given that constraint, a neuron wants to transmit as much information as possible. No, and so if this is the idea, then we need an operational definition of information. Now, there are alternative measures of information on top of Shannon information, but Shannon information is the kind of information where we say how much information can we get through a channel where we have a sender and we have a receiver. that kind of maps on how we might think about the brain. Like where you can say, I'm a neuron, I transmit something. There's something that I know that other neurons need to know. And therefore, I kind of need to get the information through the channel. And the channel capacity is limited because, well, every spike costs a certain amount of energy. In fact, there's like beautiful work where they try and count that, where they're like, okay, if I have a spike, what happens to the neuron? Well, I need to take the membrane potential, which normally sits at -70, and I need to kind of charge it all the way up to the top of the spike and put it back down, which means that I need a certain amount of current in and a certain amount of current out, which means that I need a certain amount of sodium and a certain amount of potassium in the opposite direction, which means that I need to have a certain number of ATP molecules, and therefore it's not good if I spike too often. And there's like a beautiful field that does those calculations. So if we start from there, you could say we can normatively justify our constraint, where we say like using more spikes means we need to like take spikes out somewhere else. And then we can also normatively make the point for some measure of information being optimized. Now, why exactly do we use Shannon? Well, that's a little involved, and I don't think we should talk about it under one. But that's like roughly the answer to this question. But thank you, Virginia. Let's talk about the second question. This is a question by Jack Dolgen, and I should apologize to all you guys. We are from so many different cultures that I will mess up the pronunciation of every single name here. And what can I do? Like you feel free to like totally mangle my name. So here's the question. I guess one of, maybe the assumption of the Y model is that evolution has sort of fine-tuned our biology behavior to maximize results. Is it fair to assume that's always true? That there even is a Y explanation in all cases, even if we haven't discovered what it is yet? That sounds like a great question, maybe for Kate, or like who's the right person to answer that?
I can kick that off. I think that the first statement that the assumption of the Y model is that there's sort of a force, evolution, sort of behavior over the course of a lifespan that has pushed the system to solve a problem in a particular way. I don't, and I'd be interested to hear what the rest of the panel has to say about the second question, because my intuition would be no. And I think that the reason why is that we're not going around the world solving all possible problems all the time. So it could be that we've figured out a way to solve a problem, but because of other constraints that we have, we haven't necessarily, there isn't necessarily pressure to solve that particular problem in an optimal way. And so one way that I think about normative models is that, okay, we're working on understanding this particular phenomena or this particular behavior. If I take into account the inputs to the system and what the goal is, can I write down what, and all of the constraints, can I write down how I should solve that problem? And that sort of gives you a starting point to compare behavior to. And if humans behave, and you want to design sort of, I personally love models that inspire experiments. And at the end of these models, it's really nice to have a set of sort of cranks that you can push back and forth and see what the pattern of behavior is of the model, and then compare that to a pattern of behavior in human subjects, or any sort of subjects when you're talking about behavioral experiments. And so I think that the answer to the second question is no. That's the short answer, and the long answer I kind of just gave you. So thoughts on the second question? Yeah.
Yeah, I just want to give an example of a non-optimally evolved system, which is essentially our eyes. The retina is sort of inside out in a very strange way. The photoreceptors are hidden behind a whole bunch of neurons, and the light gets filtered essentially before it hits those, which is really not optimal in terms of vision. Like the other way around would be much better. We would have much better night vision, for example. And so this seems to be, and so I don't know what the answer exactly is here, but I think a lot of people think about it in the sense that at some point, evolution took a turn and got stuck with that particular solution, and there was no way to reverse it. And that's why it is the way it is. So the answer is often no, and maybe the one of the goals of developing these Y models is to figure out in which cases we're not obeying a certain optimality criterion, and then we can try to ask why.
That's actually one of my favorite ways to use Y models, is to say, oh, well, here's the normative thing. Here's like what the mathematically perfect system would do. But here's actually a better description that fits our behavior or our system. Mm-hmm. Like, why is that the case? Why is this weird, like, kludged together, like half solution actually the way that we're doing it? And so you can actually ask and answer really like cool questions about the problem that the system is actually solving, instead of like what we think the mathematically optimal thing that it should be solving would be. So it's kind of like breaking the normative models and seeing if you can break them in the same way. I like that.
Let me just try and produce some clarity there. So basically, do you believe that evolution makes something optimal? Never. How would that be possible? No, like basically, evolution makes things better, but like there's typically very wide minima where like there's like lots of solutions that are like pretty good. No, like human vision is like actually pretty good outside of the blind spot, maybe, and the blind spot's pretty small. Like so basically, there's no way that we should expect it to be optimal. But there's something that is beautiful about these models, which is that we can meaningfully think about it. You know, like we can, if people just say research about like people walking, like we can kind of speculate, well, if you walk, you shouldn't waste your energy. You also shouldn't break your bones. And these like simple why insights actually reveal a lot of complexity that we can actually understand meaningfully. So it's not optimal, but like keep in mind that our like how models also no model describes all the variants, and it shouldn't. And like in particular for normative models for say evolutionary new behaviors, like it shouldn't be optimal.
There was a great question last night in the Asia Q&A that was kind of about that, which is like, how do you know if your model is right? And the answer is like, usually it's not. Usually it is wrong, but if it's wrong in an interesting way, then you can still learn something.
I think all models are wrong.
Yeah,
it's just
so we went into the
viewers.
We went into the classic answer to that, but I think that it follows on this very nicely, right? That if you discover how your model is wrong, even if it's your normative model that's wrong, then that's also really interesting.
So the model's wrong, like people always say, yeah, all models are wrong, but some are useful, which is sort of like, sure. The reason why models are wrong is because models by definition are an abstraction of reality. And as soon as you abstract, you remove, right? You remove things that you're not interested in. You remove things that you cannot describe. You remove things that you don't even know about. And as such, they're models to a certain degree of approximation of the reality, but they're never the reality. Otherwise, it would be called reality and not a model. So they're always wrong.
Yeah, and there's a corollary that comes from that, which is because all models are wrong, proving a model wrong isn't actually so interesting. Like there is this big excitement about falsification in science. And in physics, that has been tremendous. But in physics, the space of possible models is small. They're like all like very short equations. If we're outside of that space, it's much more pragmatic. You know, like the space of models that we deal with in psychology, cognitive science, neuroscience, it's a very big space. And therefore, like if we're willing to acknowledge that all our models are wrong, then if I say, well, it could be model A or model B, then disproving A doesn't in any meaningful way make B very likely. And you find this logical mistake all over the neuroscience literature.
Including in my own work.
I've been there, done that. I didn't get a T-shirt for it. But I did just order my organizer's T-shirt for the NeoMatch Academy because someone drew a really gorgeous.
There are organizers' T-shirts?
It says it won't be much work on the back. I really want one too, that we can get them in the NeuroStars thread, right? Yeah.
Yes, exactly. Someone in your stars is sharing that for the organizers. So in any case, hopefully next time I lecture, I get to, I do a Q&A, I get to show off my new T-shirt. But so let me read the next question. So this is a question by Liu Shuzi. And the question is, this is a question from my part about the material today. We learned in tutorial 1 that the interspike interval distribution is roughly exponential. Since the exponential distribution is the PDF of time between consecutive Poisson events, does this imply that the spiking of the neuron at hand, not presynaptic ones, is generated by a Poisson process? No. Okay, let me first answer the first one. Now, it's right that if we have a Poisson process, then because it has this randomness and everything is independent, technically it would be a Bernoulli process, no, where you could say, basically in each very short time interval, I have a certain probability of spiking and a certain probability of not spiking. But does the reverse hold, that if I have an exponential distribution of interspike intervals, then things would be Poisson? And here's the counterexample. I take all the interspike intervals and then I order them. So what happens is that the neuron goes like click, 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 very fast, and then click, click, and it gets slower and slower, slower and slower over time. In that case, it has exactly the same interspike interval distribution. It just has the fast ones early and the slow ones late, and that's not a Poisson distribution in that sense. And so that's that. Yeah, and it's important to realize that just because if it's a Bernoulli process, it produces an exponential interspike interval, the reverse isn't true. The inverted one is true. No, if it is not an exponential distribution, it cannot be produced by that process. But it doesn't go the other direction.
Sort of like a correlation versus causation question almost here.
Oh yeah, and we have week 3, day 3 to the whole causation component. So hold on, there is another question here. If so, in tutorial 2 for the model where only excitatory input, Poisson of lambda is inputted, why isn't the spiking of the neuron from a Poisson process anymore? Well, yeah, I don't know. In this case, we have a process, Poisson, that's integrated over time. And the process of integration makes it be very non-Poisson. I'm not sure if I'm good at explaining it.
Yeah, this is a hard one to explain intuitively without actually walking through the simulation. But the idea is that as soon as you start integrating, you're essentially transforming the sort of these random events into a random walk. And that random walk essentially has a certain statistic that is potentially very different from the process that generates or controls the random walk. And that is why you don't get necessarily a Poisson, or typically you don't get a Poisson process out unless you have perfect leakage.
Great. So why don't we go to the next question? The next question is anonymous, and it's a philosophical question. So in Y models, we start out taking for granted the optimization in general and the entropy in the specific example. But why is optimization used to answer the Y question? What is the philosophy and bigger idea behind the Y model? Who wants to take it?
I have to process this for a little second here.
Yeah, I'm actually not quite sure what the question really is. I mean, when you ask the why question, you typically want to understand the underlying principles. And of course, when you talk principles, it's sort of like, what do you understand by principles? And what does even understanding mean in a certain way, right? So to all of us, understanding means something different because we can understand at different levels. For example, depending on our interests, we might be satisfied with an understanding of behavior or not. We might say like, no, understanding to me means how the synapses that feed the neurons, etc., actually generate that behavior, right? And so I feel like here it's a little bit going in the same direction where when you ask why, you might have an interest at different levels here. But ultimately, you want to know sort of like what is the underlying fundamental reason that something happens.
Yeah. So the why models usually have the following logic, where you say there exists a problem, and we believe that that evolution should have found the best solution to this problem, with constraints and so forth, and of course not the optimal, but a good solution to that. Okay, but finding a good solution means that we take the thing that the definition of goodness, the so-called cost function or objective function or utility function, that we take that definition of goodness and find a model that makes this be at a high value, like that finds the good solution to us. If we talk about walking, we need a process that says of all the ways that I could walk, this is the one that say maybe minimizes energy or something like that. And this is where optimization comes in. Optimization comes in because the problem's definition is usually in terms of a scale. Now, if we'd be in a binary world where it's like either you achieve it or not, then optimization arguably goes away. I just try a few things until I achieve it. But that's usually not the flavor that these problems have in behavior. Cool, but I think it's a very interesting philosophical question here. Good. So here we have a question of Igor Zverev. 280 thoughts neuron is just the best. There are a lot of neurons with roughly uniform distribution, for example, 160 and many more. Why? We figured out it is not optimal. Is that okay for us to make a model with exponential distribution? Also, the 280 thought neuron seems to be so perfect, and there's a huge number of neurons which are significantly different. Is it okay to judge by the 280 thought neuron? We assume that nature is optimal, but what if that is not entirely true? This is a great question. Who wants to take the question of basically, we selected a neuron. Why did we select that neuron?
You're at the tutorial.
I can give
I don't have an answer to this, right? But I think you wrote the tutorial. This is written about the 283rd neuron, Konrad.
Okay.
Why not?
So let me tell all of you a dirty secret. You will find across neuroscience lots of models. These models never do perfectly if you look at the diversity of neurons that really exist.
Wait,
almost never.
What? Really? Really?
No, but the level of that, for people that are new to neuroscience, they are not aware of the degree to which that is. Now, if we say neurons are exponential, yes, if we average all of them, it kind of looks pretty exponential. In the typical neuroscience paper, you have in figure 1 or 2, you have something like typical neuron is what it says. If you do a reanalysis, which is progressively possible because people share their data, the typical neuron is never typical. It's the neuron that is closest to the theory that people are writing about. So basically, these outliers are always there. The typical neurons that perfectly fit the model oftentimes don't exist. And the model just describes behavior in broad strokes. And that's Gunnar talked about it earlier. And we have these we have these models that are kind of approximations. They're untrue, but they kind of capture something that is common. Gunnar.
Yeah, so you can even say when you played with the EI balance, right? The EI balance is sort of on average true in the brain. But if you look at the papers that actually look at the EI balance, the average is pretty much 1-to-1, but then the standard deviation is huge, huge. Like each individual neuron is like, they're all over the place. And like as a population, it's fairly balanced, but for an individual neuron, definitely not. And so you can, if you play around with the model you built today, and you change the eye balance essentially, you will see that you get all of a sudden different statistics out of it. And that's sort of like part of it. But there's other factors, of course.
Kate, you were also.
Yeah.
Hey, Kate, why don't you go next?
I wanted to know, I sort of feel that the field is making a transition right now to trying to consider populations of neurons instead of individual neurons in this regard. I think we spent several decades looking, and because of limitations of how we were recording and what we were trying to learn at the time, that we were recording individual neurons or small groups of neurons at a time, and then trying to characterize basically sort of what individual neurons do. And now there are more groups talking more about like what do big groups of neurons do together, which is really, these are questions I think I'm more interested in, which is like, how does the brain support our behavior in our everyday lives, both sort of visual processing and also like our cognitive behavior. And these are all super interesting questions and are probably why a lot of us ended up here, both the four of us here and then all of you out there asking questions. And so I'm going to bring this back around. So what I would say specifically about this question is that there are a lot of people now that are starting to think more carefully about ways of characterizing neurons that captures the diversity of responses in a population in a particular area. It's no longer sufficient to just say, oh, this is middle temporal area. Sorry, this is area MT. In the brain, it does motion, right? Because these 45 neurons are well tuned to motion in a particular direction. It turns out MT is pretty responsive to motion, but it's not like every cell that you hit in MT is going to do that all the time. So, and I think it's too, and this is related to some things we've already been talking about, we don't always, we stick our recording devices into brains, onto brains, and we set up these paradigms to ask questions about what particular brain areas do, but we're kind of, in many ways, shooting in the dark, right? We don't, like, I work a lot on representations, and when you're looking for a representation, you're assuming that the set of features that you've started with are the right set of features. And so, you know, those neurons that aren't firing very much or don't have the classic presentation, you can't say they're doing nothing. You haven't, like, we don't know what the population is doing. You also don't know, even from the perspective of looking at the responses of individual neurons, what if you showed a different stimulus? Like, what would happen then? But narrowing that down is really difficult, which is why, which is another reason why I think we're moving to these, thinking about bigger populations and describing sort of a macro, higher level processing.
Yeah. Can I follow? Yeah. I think that's it. I totally agree that like this is where the field is going, and it's also because we kind of initially in our early electrophysiological recordings, like in CAT V1, it was like, oh, look, this neuron spikes to vertical stuff, and it really likes vertical stuff, and that was like really easy to understand because us with our like, you know, relatively puny capacity for understanding, we were like, great. That is the feature that this thing likes. And the other ones are just noise. The ones that like don't do something that we understand, that's just like our recording system messed up, or I don't understand, and I'm going to bury that in supplemental, and I'm going to just show the pretty neuron that likes the vertical stuff. But I totally agree that now we're going towards the, not just the population level, but also that like the heterogeneity is not just noise, it's meaningful. And that by studying which neurons do what, we actually might learn something really interesting about why the brain is organized that way. And also, this always assumes that our spike sorting was right. So that's a whole other level, right? So like we assume that like this spike rate is actually the true spike rate, but like all we have is this crummy electrode that we stick in this particular spot in the brain, and maybe like the signal is not perfect.
Mm-hmm. And so just to tag onto that one more time, I think in remarking on the sort of early visual neuroscience and early physiology, we got incredibly lucky that the early visual cortex was so accessible in so many mammals, and that it was so systematic because we learned so much And that sort of prepared us to embark on these bigger problems now.
But it's also limiting how we're thinking now.
Yes.
Because now we go and we stick a Utah array in like prefrontal cortex where we have this mixed selectivity and we have these population codes and we have all this like complex high dimensionality of representations.
And we try tuning curves.
We have no idea what we're looking at. Yeah. So it's kind of, we got in this paradigm where we went looking for neurons that like one thing, and they have these really beautiful tuning curves to the one feature or the one set of features that they really like. And it's hard to get out of that because it's so seductively attractive to be like, I get it. I understand what this neuron is doing.
But I just want to point out a mistake of that literature from my perspective, which is, it's right. What they do is they take a stimulus, maybe they take a bar and they rotate the bar and they go like, firing rate goes up and it goes down and it's super reliable across lots of neurons. But that experiment does not establish that the neuron doesn't care about other things. For all that we know, if we change the color, the context, or all kinds of things, or the fact if the animal is walking or not, everything is going to be very different. And I think in that sense that field has systematically misinterpreted the findings. So the neuroscience, systems neuroscience looks back on a history of you change one dimension, you find that it affects the firing rate a lot, and then you assume that all the rest doesn't. It doesn't matter. And like, I think that logic is just not justified.
Can I throw another wrench into this? Sorry.
We like wrenches. Go ahead.
So when people look for representations, it very often is sort of like an end goal because the neuron cares about something, right? And that is just a fundamental mistake in my opinion. Neurons don't care about the outside world. Neurons don't see the outside world. Neurons have no consciousness about the outside world. Neurons are devices that compute. Sorry, Megan.
I agree with you.
but neurons are devices that compute, right? So Konrad wrote an excellent paper on the microprocessor that is very much like thought-provoking in with that respect, which is essentially asking, if you're randomly tapping into a microprocessor, can you understand it? And the answer is like it's very, very hard at least, and the brain is 1,000 times more or more complicated than that. And so what we're doing with receptive field mapping is essentially something like sticking an electrode into a microprocessor and asking, well, now I'm going to look at the the gates or the gate times and try to understand how the brain works. But it doesn't tell you anything about a computation, about a transformation of information that somehow takes sensory information and does the one thing that the brain is supposed to do, generate behavior.
Great, cool. We have a lot more questions to go to. So here we have a question by Yao Yao. The Rising and Song Kai Wu says they wanted to ask a very similar question. So the rising part of the ISI histogram was not modeled. Definitely isn't modeled by the exponential function in the tutorial. Is that part interesting? What do you guys think?
I can answer that if you want. So yes, that's correct. We did not model that. And yes, it is interesting. And the first thing is that you can ask, well, why is the ISI histogram not actually following the exponential function? What's happening there, right? So you can ask all kinds of questions about this. And the quick answer, and I think I said that very briefly in one of my intro slides, is that neurons have a refractory period. And if you take a refractory period into account, then you can actually also describe the rising part of the ISI histogram. But that's only one possibility. There might be other ones.
Yeah, that's a good number. And yes, this is, I mean, like, I need you to understand that here on day one, we don't do all the things that are interesting about spike trends. That would be bad for my career if there was all the things that were interesting about it. Spikes have so many aspects that literally 1,000 professors are spending their entire lifetime trying to understand them. And that means, yes, the rising flank is just as interesting as the falling flank. It's just that the models are maybe not quite as simple for that. So here, what else do we have? We have answered this question. So here is a question by Michael Cohen. What is the origin of this what, how, why distinction in computational modeling? I think it's a cool way to break down models, so I may want to cite this in the future. Who wants to talk about the history of this?
Well, it was first introduced by Peter Dang and Larry Abbott, I believe, in their 2001 textbook. So that's sort of like the standard textbook, I guess, in computational neuroscience. It's only one way to really classify models. Only one way to think about, what type of model is a particular model, what type of approach am I currently using. There's many different ways you can use. You can use scale, for example, right? So what's the size of the system that a model describes? Some of you might have heard of David Marr's classification scheme of computational, algorithmic, and physical or implementational, which has sort of parallels with the Dang and Abbott classification scheme, but has subtleties that are different. And you can imagine other ones that sort of like go in orthogonal directions. The important part here really is not so much to think about, and of course there's models that span different, like this model can be how and what, or why and how, and typically the what is always included once you get like to the higher levels. But the idea is that it's not important necessarily to come up with the perfect classification system. Actually, that doesn't make sense at all. But the importance is that to realize that the different types of models have sort of their individual different superpowers. And knowing those superpowers and the limitations of these kinds of models is very important when you try to understand what they can provide to you, and when you try to achieve a particular goal, to answer a particular question. So this is essentially what tomorrow will be all about, is to define those questions correctly, to find the goals, and then as a function of that, actually choose the right type of modeling that actually answers that. So, and to do that, you have to, of course, understand what different kinds of models can buy you, and that's what today was about. And hopefully, you get some insight about this.
And I think tomorrow also there'll be like this introduction of this iterative process, right? Where you don't just do a how model and then like call it a day. Like that's not usually the way that this works. And so if you want to really dig into a phenomenon, you usually end up with the what and the how, and also like multiple scales maybe, or like something else. And and each piece of the model can answer different types of questions and achieve the different goals. So that's something that we'll talk about tomorrow.
Great. So I want to say the hour is over. So anyone who has like a meeting somewhere, don't feel bad about leaving us. Like, as opposed to like an offline conference, this is like not awkward at all to just close the call. I am positive no one will look funny at you. You will not block the view to the stage for anyone, so you can just we will go like a couple minutes extra because that's like the modal distribution. We will go like maybe 5-10 minutes extra, I think. But definitely don't feel bad about like just abandoning us here.
We got an extra person in response to that. They're all still here, and now there's an extra person too.
Great, yeah. So here we have a question by Lin Chi-Sang. Typical models of neural coding assume a rate code, and if I understand things correctly, features such as interspike intervals are usually ignored. How does the analysis we did today reconcile with rate codes? Are there interesting examples of neural coding using spike timing? So who wants to take Lynch's question?
I can take it if you want. So first of all, the what and how, that does not ask at all about information transmission, right? So when we talk about the precise spike timing, we're typically interested in or the spike rate per se. We're asking essentially, how does the neuron transmit information? Is it just by some average firing level, or is it by the exact times, right? You can imagine that if the time is 1 millisecond, that codes for I want to eat chocolate now, and if the time is 10 milliseconds, I need coffee now, and then if it's 100 milliseconds, then I don't know, maybe I'm tired now, something like that, or I need beer. So that's essentially sort of the difference between the rate and the time codes. And we haven't asked that question really. The only time we have asked that question is in the Y model, but we have sort of like not given you a choice. We have just assumed that time coding exists, that the temporal code exists. And then we have essentially asked, okay, if it exists, then what's the best way to code the information with a given number of spikes so that we can transmit a maximum amount of information with those limited spikes that we have available. So that is sort of what I would say as an answer to this. So we haven't ignored, or we haven't really addressed actually the fact of whether one or the other is used, or how that is, or whether it's a mixture or anything like that. We have totally kept that open. We have just made some assumptions, and then we have run with that.
Right. So it's the opposite of a rate code. Now, like just to be clear, the question that our specific Y model does is, if I view every interspike interval kind of like as a code word, what kind of a model gets most information through it? Let's